We're going to have a little shift. Now, when we quit right before lunch, we were doing the composition analyzers. We talked about GCs. Most everybody has heard about, there is a BTU analyzer. They're common. They're all over the place. Those who have them like them for certain reasons. There are some historical stories, anecdotal stories of some moments of frustration with BTU analyzers, especially in chemical plants. I don't know why, but chemical plants like to use more nitrogen than refineries. So the chemical plants, if they flood their header system with nitrogen, there's not enough calorific value to keep the flame alive inside the BTU analyzer. So when you need that data point the most is when the BTU analyzer doesn't seem to work. So that's most unfortunate. What else can I talk about analyzers? We weren't going to go through the GC mass spec stuff, only because it is so rare, right? We talked about that a little bit before lunch. There's a few people who have them. It may not be your first choice, or maybe it is because of other reasons, but we can talk through the pros and cons of that. You've heard, I'm going to give something in the spirit of full disclosure, Sage Environmental and Clean Air Engineering, good friends. Together, a year and a half ago or so, we started this idea of collaborating on flares, right? So we've been doing a lot of fun flare stuff together over the years. One of those fun endeavors was the acquisition of a little company called IMAC, IMACC, Industrial Monitoring and Control. IMAC does a lot of interesting, cool, fun environmental monitoring related things. One of the things that we saw was as a need was something that could respond faster. And so Dan Pearson, Scott have done some flare studies, done some flare testing, definitely see the need for something that can operate fast and give you quick results. But it needed to include the all-elusive nitrogen, that ever-elusive diatomic molecule that frustrates everyone to death, that we need to know for the calculations. So it was really an interesting day. Bill Pierman, an employee of IMAC, and I'm going to have Bill come up, walk this way as I'm talking about, and this is his intro. We had a little chat around the coffee pot in the little lobby workroom area, and everyone was throwing up, here's our problem, here's our problem, here's our problem, and the collaboration is a wonderful thing. This man came up with a brilliant idea and started bouncing words around that none of us have ever heard of before, and next thing you know, within a year, a miracle has happened. So the process, I think, in less than a year, it was a year ago at 4C that Scott and Dan Pearson presented a flare study they did at a small chemical plant using some other instrumentation and what the results were. And based on that project and those issues, IMAC has been able to come up with a really interesting solution. So I wanted you to hear about it. I think it's a game changer. And I just want to hand the microphone over to Bill. He's going to talk you through it, and hopefully all you smart people will ask some really good questions.
Thanks.
Because we got to make our Nobel laureate here sweat a little bit.
Thank you, Troy. Okay, so I'm in a hotel with a microphone. If a karaoke machine shows up, I cannot be responsible for my actions. So, well, as Troy introduced, I had the privilege of coming on to IMAC a little over a year ago. And then at this conference, we were at a dinner, and Scott said, hey, can Raman measure nitrogen? I was like, yeah, what do you want? Rotational, vibrational, row vibrational? I can do it all. What do you want to do? And so I started thinking about it, and it's like, okay, well, why stop at just Raman? Why not just combine, because we're an FTIR company, why not do both spectroscopic techniques? And then we can start throwing all kinds of buzzwords together. So the discussion points, Troy talks, I'm sure y'all know this. I'll go ahead through it briefly. And this is underscored, very brief spectroscopic background. There will be no quiz that follows. I did spend 6 years as an instructor at West Point, so I'll have to regress a little bit and stop and not ask questions or stomp my feet. We're going to talk about Fourier transform and infrared and Raman, and then we'll talk a little bit about the instrumental design, some packaging, show you some data, and then we'll open it up for discussions. I was told that I don't have to worry about saying feel free to interrupt, but I'll go ahead and say feel free to interrupt, and then 3 hours from now we'll be ready to go. So this is something I'm sure everyone in this room already knows, what the needs are. Here, nitrogen and hydrogen, our homonuclear diatomics we'll talk about. Being able to determine this calorific value, BTU for scuff, the molecular weight calculations, the density, what's going to the flare header as far as your composition, and being able to speciate a large number of gases, because everybody knows there are things like tunable diode lasers out there that can go after specific analytes. Is there a way to get a broad coverage of analytes in a single instrument? And we believe that we can do that and do that efficiently and effectively using both FTIR and Raman. But here's what we really love to do. So whatever your concerns are, whatever your sampling environment is, whatever your analytes of interest are, we love to help you solve those problems. I like to joke that, you can't go to IMAC and look at our shelf and we can't pull off the UmptyQuat. Because you can't come to us and say, well, here's the UmptyQuat. This is what you need. This is all we got. We like to address each individual needs and requirements and then meet those requirements. We just kind of wired that way. We love to solve problems. Hopefully not create any. So I'm sure we've talked a little bit about this in this environment. There are things out there right now, flow meters and gas chromatography. I'm an optical spectroscopist. I'm an analytical chemist by definition, but you really don't want me mixing chemicals. But as far as gas chromatography, I always like to refer to any chromatographers in the room, I'm sorry, they're the separatist in the world because there's a separation science. But I do understand what the gas chromatography is capable of doing, and I appreciate what it's capable of doing. And I'm not saying it's wrong, but we're looking for something a little bit faster and a little bit, hopefully, less costly in the long run. So, spectroscopic needs, or any one of these spectroscopic techniques, a potential solution to the needs of the environment. So we're going to concentrate on FTIR and Raman. Does anybody know FTIR and Raman? Anybody familiar with the techniques? Okay, a couple people. All right, good. Teacher slide. All right, you gotta have the historical perspective. All right, don't you all wish that solving problems were this simple? It would be a lot better, but that was pretty complex when he came up with this. It's black here, it's black there. Oh, but the temperature still goes up. There must be something there. That's why I love spectroscopy. We're one of the only sciences that deals with observations that drive the theory. Not theory and then go look for observations. So William Herschel identified the infrared radiation by this simple test. We can feel it, but we really can't see it. There are some people's eyes can go a little bit into the IR, but for the most part, we really cut off at the near infrared. So, molecular vibrations. What happens when infrared radiation interacts with a molecule of interest? Here's carbon dioxide, and you can do the math. You can figure out there should be 4 vibrational modes for carbon dioxide. Now, those 4 vibrational modes are shown here with this asymmetric stretch, a symmetric stretch, a bending vibration, and then a rotational on its axis. Now you'll notice that there's one peak here, one group of peaks here, and this right here is what we call a combination band. So if you take these 2 peaks right here and crush them together and move them at a shorter wavelength, that's what you're looking at. So why don't we see anything right here? And why don't we see anything down here? It's because those particular vibrational modes are not infrared active. Doesn't mean they're not there, it's just that IR cannot, quote unquote, see those molecular vibrations. So this is what we're looking at for IR, which is mainly asymmetric, and we'll talk about Raman as mainly symmetric, and I hope you'll allow me that leeway. But these homonuclear diatomics, nitrogen, hydrogen, oxygen, chlorine, bromine, and fluorine, and so forth, do not have any vibrations that are infrared active. So they are technically or theoretically or actually invisible to infrared radiation. So that's why the GC providers were doing fairly well, because FTIR could not see these species. No species are of interest. Which leads us to Raman. Raman is a light scattering technique, which means that the molecular vibrations that are going on in the molecule, there's some absorption of the laser energy, and the laser energy is scattered, and you're actually measuring that change in laser energy. So it's a light scattering phenomenon. It is a molecular spectroscopic technique. That means you can tell how the molecules put together, unlike atomic emission where you blow it apart and you know there was some nitrogen, some oxygen, you had no idea how it went together. The electronic environment of your molecule will change your shifts a little bit so you can actually determine what, not only how the atoms are put together in a bond, but also the electronic environment itself. Qualitative and quantitative, but it is a relatively weak process. The buzz phrase for Raman is only about 1 in a billion photons are scattered inelastically or provide that Raman information. But with today's technology, that's more than enough. Some of the data I could show you now that takes a minute used to take 3 days of continuous collection, but we've gotten a lot better in our quantum efficiency of our detectors and our laser sources. So that is what Raman is not. So no, I am not a very good speller, that's why I'm a chemist, but there is a slight variation there. So what is Raman in some cartoons? If we take a simple sampling environment, a sample vial and a clear liquid, and here it is blown up for us a little bit, and we pass a green laser beam through our sample, what did we learn? The green laser beam went through our sample, and the green laser beam came out of our sample. Nothing. We learned nothing. That's called elastic scattering. That means Rayleigh scattering. However, if you were to take a notch filter that absorbed the green radiation from your laser and hold it up to the sample vial, you would see something like this. There would still be a line, but it would be a different color. And that color of that line is what Raman shift is, or what Raman spectroscopy is. You could have done this in 1928, you would have had a Nobel Prize. This is how C.V. Raman actually discovered the Raman technique. So, understanding the types of results that we get from the Raman. There are 2 different main groups. One is the vibrational spectrum. The vibrational spectrum gives you your molecular fingerprint. It's very specific to each vibration as the molecules put together. This is cyclohexane. This is one of the standards that I always use when I was doing liquid because I know where all the vibrations are and I can make sure they're calibrated. This peak right here at 801.8 is actually the ring breathing mode for cyclohexane. So it's the ring going in and the ring going out. So this is what a fingerprint would look like for a vibrational spectrum. You also can get a rotational spectrum. Now, rotational usually occurs very, very close to your laser. So it's usually very difficult to obtain a good rotational spectrum of your diatomic specifically because the laser energy has to be completely nullified. And there are ways of optically filtering to make that happen. That's actually how I collected this particular spectrum. With the exception of one homonuclear diatomic, and that's hydrogen. Hydrogen is unique, and it actually helps us in our quest to measure hydrogen using this particular phenomenon. So, allowing me a little cartoonism here, if we think that FTIR active molecules are mainly asymmetric vibrations and Raman are mainly symmetric vibrations, if we have all the FTIR molecules in the world and we have all the Raman active molecules in the world, we will have this crescent here. And who lies in that crescent would be our homonuclear diatomics. There is a crescent over here as well, but not relevant to this discussion, and I don't really bog down too many details. But this is Raman only, and that's why we wanted to combine the 2 techniques together. Not lose the sensitivity and selectivity of your FTIR, maintain that, and add not only these homonuclear diatomics, but this green overlap that's underneath the red of all the other Raman active vibrations, like the carbon dioxide. So, we have the technique. What's the solution? Well, in a nutshell, my idea was to take and steal Raman off an FTIR white cell, which is a long pass cell, 10-meter cell. Not optimized for Raman, but we had them on the shelf. Can we still get Raman off of those cells and still maintain the capabilities of our FTIR using the same cell, which was the original path that I walked down? One cell to do both. It turned into this first unit, and I literally scavenged this off an instrument. I took these parts out of the trash and assembled it. And it worked. Somebody told me downstairs, sometimes the simple solution is the best solution. So get a wire brush, clean some parts off, put it together, and lo and behold, it actually works. So in this particular configuration, we were using one cell to obtain both FTIR and Raman from the same sampling volume, which is good unless in a 10-meter cell you have a high concentration of FTIR absorbing species or IR absorbing species, because then they will dominate and absorb too much and you'll lose that spectroscopic fidelity using that cell system. So simple solution, 2 cells. So that is also a possibility. Which leads us to this instrumental design. It looks like my daughter's driver's test. I don't know what the green and hopefully the red was good and the green was bad. But she did pass, so I guess it's okay. So this is what the instrument looks like if you have a 2-cell configuration. You have your FTIR modulator over here, beam path here. You could put a cell here, or you could put a small cell here for the FTIR. Comes over to the detector. The Raman is a laser, goes through the white cell, comes out, focused to a fiber optic, and over to a simple CCD-driven spectrometer, TE cooled. And this little guy right here is a little diode laser that I've added recently to allow me to have an internal standard consistently in my Raman spectrum in case there is any reduction in the quantum efficiency of the detector. I'll realize that by monitoring the internal standard. So it gives me the ability to internally calibrate each individual spectrum. As far as FTIR goes, this is a Heaney stabilized laser which actually establishes your X wavelength for an FTIR spectrum, if you know that. There is no X axis for an FTIR spectrum. It's all relative to the mathematics that come back from the crossing of your Heaney laser. So it internally calibrates. So that is a very good addendum or good capability for the FTIR. So, just like I always get accused of, if something works, I always tear it apart and turn it into something else and make it better. I'm never satisfied with leaving it alone, I guess. So I took that system and put it into a rack mount system, mainly because there was some people we've talked to, footprint. It's all about footprint, right? We don't have the room for this thing to sit there. Can you make it vertical? It's like, yeah. So can you make it class 1 div 2? Oh, yeah, I think so. First step is to get it vertical. So now we have this instrument downstairs. This is a 3R, NEMA 3R container. And each individual shelf has a component. The bottom shelf has my FTIR modulator and the electronics to drive it. The second shelf has my FTIR cell. Right now it's about a 5 centimeter cell for the high concentration application. Our third shelf is electronics and gauges. You have individual temperature and pressure for FTIR and Raman, spectrometer, even a little computer. I don't know if y'all seen these little computers nowadays. They're phenomenal. They're only about yay big. And it sits right back there and runs the whole system. There's one plug that comes out of here, plugs into the wall, and it's self-sufficient. Up top is where all the Raman happens, your Raman laser, your my internal standard laser, the Raman cell, fiber optic taking it down to the spectrometer. And believe it or not, I don't have a degree in U-Haul moving, but have you ever walked across those ramps at a U-Haul? Like 7 billion ridges per square inch, I don't know why. But we actually rolled this across there, rolled it in here, put it up, and started it up, and no change in calibration whatsoever, no shifts at all, which I was very happy for. I expected to get some shifting, but just powered it up, and she started rolling with no problem. So what does the data look like coming off to the user? I love this slide because this helps me to also illustrate the difference between an IR vibration and a Raman vibration, because this is collected simultaneously. On this side is my IR, and on this side is my Raman. Now you can see I've taken the background. There's my background of single beam, and there's my absorbent spectrum. My FTIR has no clue that anything is in the cell right now. But I am flowing 100% nitrogen. So there's my Raman nitrogen peak, 2331, and while FTIR does not see it. So just the way I like to illustrate the selection modes or criteria for the two different techniques using this particular slide. And I can arrange this. This is all internal to our software. We can arrange it however you like to arrange it. I've already rearranged it because I didn't like the way this looked. I can make it better. I guess there's a trend there again. So other plots you can have are constant concentration data. Each one of these dashed lines, they are error bars to the fit. We use a common least squares fit to the data. So it gives you not only the accuracy and the precision of the data, but it also presents it in a usable format that some users like to see, that waterfall plot of different concentrations as a function of time. So, great, it works. It works. Can we then prove it works using more laboratory data? Well, these are some of the analyte sensitivity graphs for the hydrogen, oxygen, and nitrogen. And you actually would expect this deviation in the slopes because there's a thing called a Raman cross-section, which is a contributor to the strength of a Raman signal. And the Raman cross-sections, actually, hydrogen has the greatest Raman cross-section and goes down, so you would expect a greater change, like you do see in this graph. And this also allows us to go back and make sure that our spectrometer and our laser system and our optical paths are still operating at where we built our calibration curves by having this as our benchmark. So luckily, we had some friends up in Palatine, Illinois, up there near Chicago, and they allowed me to pack an instrument up, ship it up there. And they had this gas standard on hand, had these constituents, and used the HOVACAL to blend the hydrogen into this. So we had a multi-component mixture going simultaneously, diluted it by using the HOVACAL and the hydrogen to attain 5 different concentrations. And we were curious, once we built the calibration curve of the Raman response versus the HOVACAL response, test it against the GC. So that sounds great, so let's give it a shot. So, lo and behold, if you calibrate the Raman instrument to another instrument, like, or in this case, another capability like the HOVACAL, it gives you exactly what you would expect to see. Okay, great. You're not learning anything here. You calibrated it to what you use, so you should get the same response. And we did. I said, okay, so great. It's working great, cold fusion. Let's hold a press conference. Let's check the GC. Oy. Who put this slide in there? Okay, so what did we do wrong? We did something wrong. But still, it's 0.96 to 0.99. Yeah, I'm saying that's pretty good. Trying to make ourselves feel better. There you go. But we actually found out that the calibration for the HOVACAL with the hydrogen was off. So we went back and redid the data, and then ran the data again, and lo and behold, that looks a lot better. 2 nines, not bad, and so we are at least as sensitive and selective, I believe, as a GC. So it looked pretty good. So I said, okay, all these people have all these GCs. Well, they don't want to get rid of them. So what if you used a GC as your QA/QC check? And then let the Raman run. So you only run your GCs every once in a while. And if you do that, okay, the same thing as before, it does seem like it's a viable opportunity for you to check and maintain your response from your Raman FTIR system. Now, why would I need that if I got the GC? Because I'm collecting data every minute or 30 seconds, depending on your concentration levels. And I don't have to change my columns because I don't have any. So, great, it worked in the lab. I've almost convinced you it works. Then we take it out into the field, and what I call the shakedown cruise. So the shakedown cruise, here is a live process flow, looking at the FTIR, and you'll notice the constituents here, all right? Some of y'all can probably figure out what's going on with this process, but this was off one snapshot in time. In the exact same snapshot in time, the Raman data was coming off. So you'll notice a couple things. Number one, you see the same species, every single one, carbon monoxide, HCN, methane, water, ammonia, not hydrogen, in the FTIR spectrum, but you do not see the hydrogen, the nitrogen in the FTIR spectrum. So this is what I was talking about before. Hydrogen is one of those unique species where you have easy access to the rotational lines as well as the vibrational line. And that actually does a great service to us using a TE-cooled detector, because the response curve of most of these detectors is kind of, a parabolic curve. And these guys are at either end of the curve, so it allows you to kind of flatten out your QE or your response by ratioing and analyzing either side. The center is always good. The wings are always a little bit less. And so now you can actually use these peaks to your benefit to help flatten out your spectral response, which is a pretty cool little feature if you have hydrogen. This is another thing that I thought was really cool. This is methane simultaneously coming off the FTIR on this side and Raman coming off on this side. Now, trend-wise, I thought it was a pretty good story. I actually got a chill down my spine when I saw it because I thought it was cool. Yeah, I'm easily entertained, I guess. But what was really neat about this was that this data here on the Raman side was a 1-point calibration curve. I was saying, I wonder, since I'm sitting here, why not just go ahead and try this and see what happens? So I took the data from the FTIR, put the spectrum into the Raman, called it that concentration, and let it run to see what it would do. And it did a great job. So this only gets better if we have a multi-point calibration that goes with, the analyte of interest. Okay, conclusions. We did have a theoretical design. We did test it on bench, laboratory, and a field environment. We have a couple more planned to go out there and use this instrument some more. It does provide some interesting capabilities. Again, 1-minute time average data coming off the instrument, or less, depending on concentrations. And it does allow us to monitor and measure all species simultaneously. Now, what I will say, because it may come up, is Raman sensitivity. What you're going to get as far as limited detection using the Raman only is about 0.5%. It's probably the best we're going to achieve right now. With FTIR, it's in the low ppms. So that can be improved. I can go to lower on the Raman if I was to build a Raman-specific cell, which I had the designs for, just hadn't really put it together yet. So, but when it comes down to 0.5% or 1%, I was told that really that's not a big deal. So if it is a big deal, we do have the capability of going lower. I just don't know how low we can go. So that is us. And like I said, good thing Troy, caveated the fact that he's part of our parents. We call Clean Air and Sage our parents. And we are right up the street in Round Rock, Texas, and we're always welcome to entertain, visit with you, see what your needs and requirements are, show you our facilities, and try to come up with any solution that we can help you with in your environments. So I guess subject to your questions, that is all I have. I like to say in the Army, any questions, comments, or ugly gestures, they're all free.
Summarize where you are in the field evaluation?
Sure. We've run one, completed, and we're waiting for a customer to come back with some more information, but that data has already been done and analyzed. We have 2 potential opportunities coming up, and I did fail to mention or maybe I mentioned that rack configuration. We're working on that Class 1 Div 2 now. I've already started the design phase with the people who are making our shelter. And so it will be Class 1 Div 2 capable, as well as rolling to any location or in benchtop. I don't know if that answered your question, but that's really...
Do you have the ability to query these instruments over the phone and QA what's going on over the phone, correct?
We do. We do have the capability of logging in and looking at the data real time. And I think we improved that by talking to the gentleman downstairs. I think it's even a better way doing what we're currently doing. So we're looking into that as well. Yes, we do it quite often. We always tell when it's raining in Houston because we log into the TPC and it's like all the water is there. And so we always know the weather in Houston. But yes, we do that. Which is why we're going to skip the intercompany. Hey, what IT don't know won't hurt them, right? No, I'm just kidding. Yeah. Yes, sir.
Many times we've looked, it's still on an applications basis. So you're talking about being able to use the technology for fence line, shooting at a flare, looking, you actually have it in the flare exhaust line, potentially looking in the future. What are the applications?
Well, right now, flare fuel, the post-knockout drum heading towards the header is where I've done the measurements. But you could do it in any process flow, any complicated gas process flow. We can help you know what you're actually putting into your process, your generators or whatever. I forget the right word. I was only process director for a little bit. But we can actually in real time tell you what you think you're putting into your process application versus what's actually going into your process application. I don't know if it's safe to say you shouldn't see any hydrogen. I saw hydrogen. They didn't know until we were there. And so even though you think you have a good idea of what's going through your systems, it's not hard to check using this particular technology.
And then to get the sample from the line to your device,
Heated trace line. And when the rack mount configuration, I've put in the capability of isolating the Raman and FTIR cells. So if anything were to go wrong, you're only going to you'll be operating at whatever only homonuclear diatomics is, or less homonuclear diatomics, because you could run just the FTIR, or you could run just the Raman, or you could run both, and you have that capability. And yes, and the heated trace lines are the way to go. Yes, sir.
So is there anything that you can't see?
Anything that I can't see?
What do you do with things that you don't know? I mean, you get a spectrum, like, doesn't match anything.
That's
That word "all" kind of creeps in there.
Okay. So let me all molecules. Okay, I'll caveat with that because I can't see atomics, right? If you have argon, it's just argon. There's no molecule, there's no bond to vibrate. So yes, I should caveat, I cannot see atomics. But all other molecules are either going to be IR active or Raman active. Now, there may be degrees in how low you can go. I can't.
You mentioned earlier he has a flare that has a lot of argon.
We'll see it tomorrow, but it has.
Well,
I don't really need.
I can do argon by difference. There we go, huh? Whoa, yeah, tap dancing.
What happens when the temperature drops to like minus 40 or so?
Minus 40. I mean ambient temperature?
No, the temperature in the flare head. In other words, it's super cool in the flare head. What happens to your system?
Heated sample.
Yeah, it's a heated sample line and a heated sample cell. So we don't want condensation. So
Right, but the flare, can be super cool in some events.
would it offend you if I heated that super cool flow before it got to my analyzer?
As long as it didn't affect the numbers.
No, it shouldn't affect the numbers. We temperature and pressure compensate. So
Although whatever condenses out in your flare header, obviously.
that's
it's not
an issue.
gonna be collected.
Yeah, that's the problem.
It would be reevaluated.
Yeah, we don't like condensation in our cells.
I don't think they vacuum the bottom of the duct.
No. No. Any other questions? Yes, sir.
What's involved in changing, if you wanted to change what you're looking for? Let's say you're looking at
Sure.
code, you're looking at reduced sulfur and you decide you want a few more sulfur compounds.
Sure. It's just a matter of updating the quantification method. We have our own internal quantification program, and so whatever analyte you're interested in with the FTIR, if there are no references, we'll generate those references, either by synthetic or getting our own gases, and that should generate the references. And the same would be for the Raman. And it's just a matter of then picking those regions where there is no spectral interference across the breadth of your spectral footprint, and then analyzing for those individual species.
Now, one test,
I'm sorry?
From a practical standpoint, you just load that into the.
Yes. And you can click and unclick. If you're really not interested in this today, you just unclick it and it won't be there. Or if you really want to see everything, you can click them all. It's whatever you want to see, we can display for you.
let's say the last test, you did HCN references, and
Yes, on the fly,
it was.
which is a bad thing if you think about HCN.
Very interesting to see how difficult it was to get HCN Cal gas. In percent.
Yeah, no one like that. It's a good thing we're at a facility where we could just dump it into their flyer line. Yes, ma'am.
For a complex stream, how do you differentiate the species you have?
Sure. If you were lucky enough to in your the fundamental vibrations and not have any overlap, then that's good. But if you aren't, then you go out to the overtones and the combination bands, and especially the high concentrations, you can go way. I'm a ramen guy, so I have to keep going the opposite way down, but you're going the opposite direction in the spectrum, and you can find those combination bands.
Well, I guess what I'm asking is we've seen a pretty clean spectrum SPR for CO specific molecules. What about when you have a hot mixture of, I don't know, thousands of, in a refinery, for example, thousands of components? How many spectra of those will you need, or what's the data?
However many are there, if you have an idea of what's there, it makes it easier on us. If not, we have books, and I love that part. But we can, like when you saw those, like the water vibrations, you got all this. You don't need all that. You can pick one line, you can pick two lines, one line here, one line there, one line there. So you're going to find regions where there's no spectral interferences. And then what's left, we can actually display the residuals of our spectra. And it's like, okay, we got everything accounted for, but this is showing up. What is that? And then go back and then try to analyze, figure out what it is. You pretty much know the regions. So
for example, CO and water, you have that big envelope for the water vibrations.
Correct.
They want to overlap with the CO stretching mode.
Correct.
1600 or whatever.
No, that's correct. If they do overlap, then you go to the overtones. So it's just a matter of digging into the references and looking at what the residuals after you quantify everything you think is there. And that's always the fun part. Is what you think is there is probably there and then not there. Like different isotopes also have caused us trouble.
You will need a means of separation before detection.
No, absolutely not. Nope, does not. I can't think of any where you wouldn't find a single band that you could quantitate off of. Sir.
Those compounds may be in the gas stream, but you really don't. If they're in parts per million, they're irrelevant to the BTU count. So there may be a lot of interesting things there that are interesting, but you don't need to quantify it. Because they're not going to add.
Don't rate EPAs at all.
I know.
Now I see where you got the. I see where you got the all problem from. Yes, sir.
What about maintenance, QAQC type stuff on the boat?
Okay. With the FTIR, we could simply just looking at it. We always monitor the source, so always know how how good the source is operating by measuring the voltage. Same with the Raman. Has its own laser pickoff, so I know the source, what it's doing. And if the laser starts to tail off as a function of time, that of course is going to affect your signal. But as long as we know what that tail off is, we can then bring it back up to our quantification level. So we can monitor that real time, and we can monitor your IR, your throughput. And if your throughput starts to go down, if you get there's been some gunk. All right, this is an optical system, and if you have an upset that throws gunk in there, and it coats the optics, then it's just a matter of getting the gunk off the optics. And even when that's happened, it really, it happened to us a little bit because we had condensation like nobody's business. But we were able to just do the plug and play and switch another one out and put it back, and we were up and running and no problem at all, no time.
Got to start a daily calibration drift assessment like we do on a GC.
Yeah, well, the good thing about our quantification program, we actually run a shift program before we quantitate. And what that means is you have your reference spectrum. If your spectrum coming off is not exactly lined up, the shift will actually line them back up and then quantitate. So any type of spectral drift will be compensated for in the analytical program. And it does that both for the FTIR and the Raman. So with the Raman, with the FTIR, it really isn't spectral drift. Per se, because of the fact it's calibrated by that Heaney continuously, that establishes your x-axis. The Raman really doesn't shift that much either, except on the wings. Like I mentioned, when you're getting on the wings of the quantum efficiency of your detector, a little problematic out there sometimes, but it's correctable. There's all kinds of dissertations out there on how that's done, and it's well known and well documented.
But there would be a short period daily calibration and validation, right?
Sure.
Switch over for a couple days every day, make sure it's
I have a manual valve on it right now, but there's no reason you couldn't put a solenoid and just switch it over, let it run through, compare it with your reference, and then if you're happy, you switch it back over to your process flow, and then off you go running again.
Bottle of gas, not 23.
Well, one bottle of gas would work for me. Hope it'll work for y'all. Yes, sir.
Yeah, I'm familiar with FTNAR.
Yes, sir.
Liquid samples and the amount of modeling that's necessary to get a good measurement. How does that compare with what you're describing?
I'm sorry, can you say the first part again?
As far as with FTNAR?
Oh, okay, forward transfer near infrared.
Right.
Okay.
Right. And I'm just wondering how your analyzer using the FTIR and ROM, what the requirement is in terms of modeling to get the accuracy.
Okay.
In a dynamic process.
Sure, and a lot of that takes place in our quantification methodology. Not only is there a shift program, there's also a linearity correction that we do for each analyte. And let's see, quantification, trying to think of the other window, but those are the two main ones. So when you build your analytical method, you have all your references and you put them into the database. And that's the other thing it's capable of doing is a dynamic reference. So if you're looking at 1 to 25 ppm, you're looking at 1 to 25 ppm, and all of a sudden you have a 5% upset. Well, the data, the program that's running will be running references 1 to 5 ppm. Whoa, this does not match. What references do I have here? Okay, I'm going to use the 10% because that's the closest one that I have. Now I'll quantitate. So we have that capability in our software package, and I think that's pretty powerful as well, because it can dynamically choose the best reference to meet what's coming off the spectrometer at any sampling point in time. So I think that's maybe answer your question, but you can build a calibration curve at 8 points, 100 points. Once you develop your linearity, it's set into the software program. Any other questions? Sir?
Do you have a guess on cost compared to DC or DBO?
Yes, I have a guess. $1 million. No. $2 million actually. I have kids. $3, come help me out. No, seriously. Right now, not in a class 1 div 1, and if with a single cell, it's $175K. If you do 2 cells, it's about $185K. If you want to increase it to a class 1 div 2, that's going to add an additional $10K or some change. So that's what we're looking at right now as far as your upfront cost. But we don't have any long-term data for I don't have access to long-term data for consumables for GC. But having worked with GCs, I don't think it's very cheap, and I don't need an additional standalone shelter for the instrument. In a class 1 div 2 enclosure, it is its own enclosure. So I don't have to have an enclosure with a monitor to monitor the monitors, so the monitors can be ready to monitor. So that's kind of the long-term benefit for this particular technique as well.
So if you were using it for total sulfur, one cell or 2 cells?
Probably still, well, that's an interesting question. Based off of where they are in the regulation, it's like 1 to 150 or 160, and then north of what, 300 ppm?
Yeah, so there's a load range of 300 ppm.
Okay.
Then we were also looking, now you know why Herman was looking at what compounds are the definition of total sulfur, total reduced sulfur, and reduced sulfur.
Mm-hmm.
Those specific compounds that make up the definition of total reduced sulfur are the ones that he had a calibration plot, each one of those individuals. And it's not a pyrolysis method, but take everything that's in it
Right.
and look for SO2. It'll quantitate each one of those individual components that make up that definition.
And to address that specific issue, we're working with some good friends there at Air Liquide to actually monitor, not theoretically, actually go into the facility and monitor those species of interest and what they are, what's the best configuration, can I get away with a single cell, do I need 2 cells, what path length do I need for the IR? I may have some ideas, but it's always trust but verify, right? Yes. Yes, sir.
Are you anticipating the MAC rule, and I see a good application of the MAC rule upcoming. Can you talk a little bit about that? Do you see the application with this for the MAC rule as it comes?
Okay, I'm gonna ask for help on the MAC rule.
Flare gas composition,
Oh, okay.
BTU, molecular weight.
Sure. Yes. Exactly what we've done already with it. So I don't know how to specifically answer your question, but
Yeah, I think it's, of course, I'm biased, so I readily admit that I'm biased. I think this is the cat's meow. So this is going to give you some really dynamic information rapidly, which is, I think, for MapCC, I don't need a SEMS, I need a dynamic control. And every minute I want to change something. The history had been, you get your analysis for BTU content. I'm going to set the flare supplemental gas at a certain point. I can't move that valve for 15 minutes. And you're always trying to guess in advance where I'm going to set that valve. I'm adding a lot of natural gas. And I wish we could have our hands on the data that we could share publicly, but it's not publicly available. How much natural gas are the consenters adding to their flares because of this issue? And if they could do it every minute, just think of how often you can try to minimize that extra gas being used. It adds up into quite literally the millions. It'll more than pay for the device. It'll more than pay for it. So it's not just buying a device to use that to tell me how much natural gas to use. We want to sell you a device that will actually reduce the amount of natural gas you have. You're still going to have to use it.
Right.
Hopefully you'll be able to use less than you would have. So I think it has huge application, specifically for CC.
that's why I make the instruments and he talks.
Biased opinion, though.
Yes, sir.
I'm kind of going to put Troy on the spot, because we've been talking about this.
Oh, thank goodness. Go ahead.
How are we working towards getting the standard conditions of permits changed such that we can implement something like this instead of the BTU calorimeter GC? Because the special conditions of flares are saying you have to have a BTU, a GC, or a calorimeter.
Yeah, so we have had a lot of good discussions with various state agencies. And in the same respect that we've had some really good discussions with EPA. And those discussions all center around a performance standard that's written from sampling a boiler stack. We're already struggling to figure out how to take those performance specs and RADAs and CGAs, how do they apply to our unique situation. Now we want to go a little bit further. Yes, I need to do a daily calibration drift, but I have no response factor. There is no gain now on this thing to adjust my response factor every day. So this device doesn't really need a daily calibration drift assessment. I don't think it does, but we'll do that if we want it to do it. And we'll be happy to share that. So it's not a problem to do a cylinder gas audit. Cylinder gas every quarter. I don't think you'll have any problem with it. And getting the agencies to agree to that, does that require an M? To me, I'm not altering an emissions limitation, so I'm trying to argue I don't need to go to the federal register, I don't need to publish that. This is just a simple AMOC, alternative means of compliance here in Texas, right? It should be a really simple thing.
Well, what Russ's response to the question? Sorry, Russ.
November Charlie, no comment.
Show me the data, show me what the record request, and the other folks in TCEQ have all said the same thing. It sounds brilliant, can't wait to see it. When you install the first one, you want to come see it. Yeah, they want to understand how they can make this work. They see the benefit of it too. They don't want you wasting gas either.
Any other questions for me or Troy?
Pressure system flare permit, so we're a long way from What's your guess on when something like this could be commercially available?
Tomorrow? Yeah, two actually.
Say the one downstairs for sale?
That's my renter, but I just we finished last week transitioning it from a bench to a rack, and so now we have all the plates. We got them all prototyped. Now it's just a matter of putting the plates together. I know where all the screw holes go, and we use our standard base plate for the FTIR. So it really looks on the surface to be quite easy for us to put them together. If I can do it, I think anybody can. Yes, it's right. Just don't ask me to solder. I can't do that very well. But I'm thinking we could probably turn them out, at least 1 or 2 a month, with no issues with our current manpower. So we're always looking to improve that. And I really would love to have that problem, actually. Any other questions, comments, and/or ugly gestures? Okay. Well, thank you all very much for your time. I appreciate it. I'm downstairs. If you want to know how much hot air you all are actually exhibiting during our little breaks, please come down and look. I'll show you a carbon dioxide increase every time. It was significant today with lunch. More than doubled our normal output, so congratulations. So I'm down in booth 1 and 2. No, none of that. It's all carbon dioxide. It's all good stuff. So come on down and see me, and I'll be happy to talk to you more. Thank you all for your time.
Thank you. Bill.
That is not mine.
Or Troy.
Okay.
All right, so now we are going to try to fly through the next couple modules so that we can fit most of what we've had planned today in for today, because we have 2 more special guest speakers. So the next 2 modules deal with the combustion efficiency calculations as shown in the consent decrees, and then the control systems that you can use these calculations to actually control the combustion efficiency for your flares. So, just brief background information here. Brian Dickens at EPA, April 2009, started to draw enforcement inspiration from this idea in Subpart A, which we went over at great length yesterday, discussing the good air pollution control practices. It's common, and the allegation here has been that it is common knowledge that steam and assist air can impact the combustion efficiency. These studies have been around since the 1980s. You should have known, essentially. Yes, this is very true. The alleged violation for anybody in an enforcement action is a failure to use good air pollution control practices by oversteaming your flare. And so what people are seeing is that they've followed Subpart A to the best of their ability, but what hasn't happened is that it's going back to this part in 60.11 where it requires sites to use good air pollution control practices. Some of the available literature. Troy touched on some of these studies in the first module yesterday. Range from the 1983 CMA study, EPA studies in 1984 and 85, various API guidance documents, and your flare tip operating manual. If you go back and look at the operating manual provided by your flare tip manufacturer, sometimes there's a specification for a recommended steam to vent gas ratio, or at the very least, your flare tip should document what your minimum steam addition is for your flare tip. And these are the sort of things we're going to talk about Flare 114 request on Thursday, but these are the sort of things that if you receive this 114 request, EPA is going to be asking for the sort of what documentation do you have in your possession that discuss those sort of things, the steam rate addition to your flare and those minimum steam rates to the flare. When you look at how do you determine flare performance, and you have a couple of obvious choices. Visible emissions. Oddly enough, a smoking flare is not an inefficient flare. A smoking flare is actually a highly efficient flare in terms of combustion efficiency and destruction removal efficiency. Those are the other 2 factors you can look at for flare performance. But how do you measure those? You can look at, in theory you can look at a flare and tell if it's smoking or not. But how do you measure combustion efficiency? How do you measure destruction removal efficiency? So we've talked, I think, quite a bit about a smoking flare, so I'm not going to go too in-depth into that. But combustion efficiency, when you have a flare, you have an open flame. in the atmosphere, you can't really measure the emissions coming off of that. So what that leads us to are this concept of surrogate parameters. And that ranges from exit velocity based, where you see the tip velocity that we've been talking about in subpart A, and also this concept of momentum flux ratio that's in the consent decrees, and fortunately not in MAX-CC. You have assist gas based surrogate parameters, and those are your steam to vent gas ratio for your steam assisted flares. The consent decrees and the OAQPS document introduced this concept of the stoichiometric air ratio, and then MAX-CC introduces these dilution parameters that were kind of totally out of left field when that was published. And then you have your net heating value based parameters, which is the net heating value, the lower flammability limit, or your combustibles content as we see in MAX-CC. As far as exit velocity based parameters go, these are based on studies from the 80s, and there are concerns about the scalability of the test. These are done on roughly some of the studies this information is based on were more or less Bunsen burners. So their scalability to large industrial flares is questionable. This picture over here is just documenting, it's from the BP consent decree, BP Whiting consent decree, and it's just showing how when you do the exit velocity, it's not your nominal tip diameter you're caring about. What you care about is the effective tip diameter. And what it's showing here is that in order to find the effective tip diameter of this flare, you actually you end up removing the cross-sectional area of each of these inner steam tubes, and also the area encompassed by the stability rings around the perimeter of the tip. So your effective tip diameter is actually much smaller than your nominal tip diameter. Hopefully this will be the only time I talk about MFR. This is just the evolution of the exit velocity-based surrogate parameters, and it's just these images here, the numbers are somewhat nonsense because the MFR limits set in the consent decrees are actually 0.0030. So calling MFR greater than or equal to 1 is somewhat nonsensical. But combustion efficiency. Now, combustion efficiency looks at the effectiveness of turning the hydrocarbons in your flare vent gas stream into carbon dioxide. So in the numerator, you have your concentration of CO2. The denominator, you have your concentration of CO2, CO, and your unburned hydrocarbons in the plume. So you have the grand total, that denominator, constitutes all of the carbon that should be in your vent gas stream, whereas the numerator just looks at the carbon that's been taken, fully oxidized all the way to carbon dioxide. Whereas destruction removal efficiency looks at if you had 10% propane and you took it to, you measure only say, 1% propane in the plume, that would be a 90% destruction removal efficiency. It doesn't matter what that 90% of propane that disappeared went to. It could have gone all the way to carbon dioxide. It could be to CO. It could be to random other hydrocarbon species in between. All it cares about is that it's not propane anymore. For the TCEQ study in 2010, this was the extractive sampler that was used to take the measurements and determine the combustion efficiency. Obviously, this is probably not feasible at most sites for determining combustion efficiency. So we had, this was positioned such that inside the flare plume and trying to pull samples from there.
You just talked about the destruction efficiency.
Yeah.
The two different terms there, destruction efficiency and
Combustion efficiency.
And from the regulatory perspective, how do those fit in?
Well, I mean, the goal is 98% combustion efficiency. So, and this is, there is, oddly enough, we talk about this a little bit in the AP 42 module that we may or may not get to this afternoon. But, in the AP 40, in the changes that have been made to AP 42, the EPA has actually shifted the emphasis from destruction and removal efficiency to combustion efficiency in one of the spots. So that's been the shift towards that. Yes.
It shows up in your permits because over the years we weren't that precise with our words, right? So some permits use combustion efficiency, most use DRE, destruction removal efficiency. They just use the acronym DRE. And really, it only should apply now, you should only apply it to an incinerator, thermal incinerator, some type of an incineration device where I'm adding fuel, creating a firebox, and I'm trying to destroy what I'm sending through that incinerator. We have to work at keeping the distinction. And
Yep.
we do have a regulatory hiccup where even some of the older state level rules reference a DRE for flares. Some of the tribal rules, especially for natural gas, keep referencing DRE instead of
And we'll talk.
The mistaken assumption that EPA has made, and go back to the one you just were at
Oh.
a second, you'll notice that the assumed hydrocarbon DRE of 98%, and EPA has said that a combustion efficiency of 96.5% is equivalent to a DRE of 98%. That's not true, but that's the assumption that EPA is going under. That's why you see this 96.5% pop up in some areas. The goal is to get that 98% DRE, and you can achieve it because DRE is always higher than the combustion efficiency. The assumption is that if you have 96.5 combustion, that's equivalent to 98 DRE.
But there's no basis for that.
There's absolutely no basis.
Let's not get bogged down in this.
Details.
I'm just saying that's the assumption they've made.
Yeah, I heard this story and I didn't understand what they were talking about. I still don't.
Can I say?
But so the TCEQ flare study, I assume most people have probably taken a look at this. If you haven't, it's a wonderful read. It's got lots of nice pictures, or at least the presentations do. But pretty much it was looking to quantify the effect of steam or air assist, and it did both, on the combustion efficiency and VOC destruction removal efficiency at various flow rates and BTU values. Now, we've looked at the exit velocity-based parameters. Now, maybe the best parameter is instead an assist gas-based parameter. Now, these values are straight out of API 521, Table 11. And interestingly enough, in API 521, they state that these are the required steam-to-vent gas ratios for these various components. Now, they're not really required because, for one thing, you're never going to flare pure any of these, so it's always going to be slightly different. But every stream is different. Your flow rates change. All of this dictates how much steam is really going to ultimately be required to efficiently combust these without smoking the flare. So it's just an interesting note that these are guidelines, but by stating required, you add a level of certainty to it that shouldn't be there.
We actually tested these in the marathon, the first marathon test, and none of them are particularly accurate. The data comparing the actual steam-to-vent gas ratios you need to prevent smoking are in the marathon report, if anybody's ever interested in looking that up.
Good to know.
This is that table on AP 521.
Right.
And that word up there, the required steam to vent gas ratio, that word required. Even though they've heard this argument 1,000 times, Scott, right?
I know.
They've had to have heard it 1,000 times. In every enforcement case, if you get invited to the table, it's like they want to start over fresh with you.
Yes.
That they want.
Well, they figure you're the ignorant one, and you don't know all this stuff, so it's.
In the CMA EPA study, we looked at propylene propane mixtures, and we ran them at moderate velocities at the 0.5, 0.6. But at low velocities, when you need more mixture, you need to skip up to like 0.7, 0.9 for that same mixture. So it's a function of the mixing that you need to get the air into the flame. So there's a lot of variables at play here.
Yeah.
And then each flare is going to be different.
Is anybody on the API committee just to help change that word? It boggles my mind after all these years, right, that we still can't seem to get API to change 521.
So this is another table out of API 521. It has again this word required steam rates for elevated flares. This is your percent weight in unsaturated hydrocarbons and your pounds of steam to pounds of combustible gas in order to guarantee smokeless capacity. So you have this lower line here is no trailing smoke, and so it ranges from call it 0.1 ish to 1.7. No smoke, it's between maybe 1.5 and just under 3. Reduced luminosity is offered up as maybe 2.8 to 3.8. So here we have steam to vent gas ratios being, for various operating scenarios of your flare in API 521, you have what, under I think most circumstances now, if we started looking at the math behind them, would probably be looked at as oversteaming your flare in a lot of cases.
Well, it's interesting, if you see the word required, you have to ask required for what?
Mm-hmm.
You know, EPA will say, well, since it's required that if you're over this, your combustion efficiency is affected. Well, this isn't about combustion efficiency.
Nope, this is
about
just,
smoking.
this is visible emissions essentially.
I
Yep.
would agree when you get up to the reduced luminosity, which is interestingly at 3 or above, which is kind of where you actually do see it drop off.
Oddly enough, you're reducing your luminosity because you might be putting out your flame.
Yeah, when you cool it off, it doesn't glow as much.
Yes.
That's the general rule.
Water.
11 was all about smoking as well.
Mm-hmm. Yes. Yeah, this was all the required steam to vent gas ratios to prevent smoking for those components.
What I'm saying is that lower velocities, and that's what we did, we used more steam that was indicated there.
Okay.
And we tested that and it was great efficiency.
Mm-hmm.
Okay, so
So these are just some graphs from the TCEQ study. This one showing the low BTU value at various flow rates, and this one at higher BTU value and the same two flow rates. And you can see the lower BTU gas starts tailing off maybe a little sooner, and the higher BTU one tails off. So you have significantly decreased combustion efficiency at a steam to vent gas ratio of approximately 1, whereas over here, that same, or a similar decrease in combustion efficiency isn't seen until a steam to vent gas ratio of 2. So, but again, this is for how those flares were operated at that moment in time. Every flare is unique, and that's part of why the EPA hasn't proposed a steam to vent gas ratio in max EC, is that.
What surprised me about this, I was expecting the curve to go a little bit further out with
Mm-hmm.
the flow,
Yeah.
right? But it didn't, and I asked the zinc guy, and I said, well, what if we put 20,000 pounds an hour through there? Would it still be on its curve? They said absolutely be on that curve.
Yeah.
So that was a surprise to me about a flare novice. So, it's all about the BTU.
Yep, BTU and the mixing of the steam.
the lower BTUs now, that triple 11 was on pure compound.
Yep.
Okay?
Yep.
That lower BTU is the incipient smoke point. I don't know what this is, but 600 or 500 is about the incipient smoke point. And then the 300, you really don't need steam for that. You can turn the steam down to minimum on those flares. You can operate them less than 0.1.
Mm-hmm.
Okay? And then on the 600 one, you're going to need steam for that, but again, it's going to be less than the table 11 chart.
Yep.
When we turned the steam off, at the 350, it did smoke, to my surprise.
On your flare.
Yeah,
Yeah,
because it is a pretty large diameter.
right.
So, but at minimum steam, it was 46%.
Right, and then on the 8-inch flare we did at 300,
It
it was
smoke.
marbled. No, it didn't smoke at 300. It was marbled. So it just depends on the flare size and the
Mhm.
dynamics of what's going on.
So let's see. So again, we've talked about this has been mentioned already, but the goal is to operate as close to that incipient smoke point as possible because that's the most efficient point of combustion. You get excellent combustion efficiency right at that point.
Now, on the method 22 question, is that a smoking flare?
Well, that is the question. yeah, that's probably smoking.
That puff is in the flame, one visible flame.
We have a very liberal interpretation of that.
So, let's see.
Bad background or something.
Not a lot of contrast.
Yeah, it's not bright enough sunlight or something.
Yes.
So, and then in addition to the steam to vent gas ratio, you also have the stoichiometric air ratio that OAQPS has talked about. And it's a direct mass to mass ratio, looking at the amount of air supplied to the flare tip and the amount of oxygen in that air supplied to the flare tip. And then you can see here, it's a much, there's less of a shelf than there was on the steam to vent gas ratio, where it stays somewhat level and then falls off. For the stoichiometric air ratio, you're adding air, upwards of 150,000 pounds an hour. There's a fairly linear decrease as you add more air. So, and the red dots there are the 900 pounds per hour flow. Those are the wrong units. Sorry, BTU per scuff in there.
Obviously premix air. I'm kidding, I don't know what premix air is.
I don't know, Russ, did you guys use premix air for the?
I don't know. Nobody sees what that was.
Yes. Okay, well, we've talked about this drawing already, the various spots you can look at the net heating value of the gas. Okay, now we're going to walk through some of the equations. Most of you guys will have seen these before, so we'll go quickly. First is the net heating value of the vent gas. It's just the summation of your various components in the vent gas and their individual component net heating value. Then you also have the inverse of that, which is the lower flammability of your vent gas, which just takes the same, the composition divides by the LFL of their components and then sums that under 1. This table is taken out of the current flare consent decrees. It's remained consistent all the way through, one of the few things that has, perhaps.
2 mistakes that are my responsibility.
I'll let you cop to them in a minute then. But anyways, what you have here is a table that lists the molecular weight, the net heating value, and the LFL of each of these components. Now, something to keep in mind here is that these are the values the EPA has prescribed that the consenters used. However, what we have seen in instruments and data processing programs provided by the instrument manufacturers, they don't necessarily use these values. They've used values that, are in the same ballpark, but they're different. So it's a matter of, if you're going to be using a GC or a IMAC device, to do these calculations, you want to make sure you're using the values that the EPA has probably said you should use. And so, it's a matter of just small adjustments within the program. One other thing to note is the 2 different heating values for hydrogen. 274 is the actual net heating value of hydrogen. 1212 is the effective heating value of hydrogen, which takes into account the flame speed of hydrogen and the fact that how it burns well and tries to boost the combustion of the hydrocarbons. So, Scott, do you want to?
Since they're not going to let us use 1212, we don't have to go into
Yes.
why it's there, but it's useful if we could get it used.
Yep. It ends up coming out in the wash in the combustion.
Similar property for CO.
Mm-hmm.
So the CO has the same problem, but you don't have the same.
Well, yeah, usually you don't see that much. Well, at least in flares that I've seen, you don't see a lot of CO. Hydrogen is everywhere. So the only time you really need it is if you're comparing data from either one flare that has a highly variable hydrogen or a series of flares that have different levels of hydrogen. It just puts it on an apples-to-apples basis. Other than that, it's not necessary.
Mm-hmm. So.
And EPA doesn't like it.
All right, so these are just this is a nose plot showing the different flammability limits for mixtures. As you combine different inerts into a flammable mixture, it'll impact the LFL of that mixture. And this just shows what happens to the LFL of a methane mixture as you add things. Helium, helium, nitrogen, water. Some of this stuff is probably less relevant to a refinery or a chemical plant. Methylbromine, or carbon tetrachloride. Probably not things many of you are going to see in your flare header.
I see a lot of helium flares.
Yeah. And also with max CC, you're not allowed to burn those things in a flare anyways now. So, once you've found your net heating value of your vent gas and the LFL of your vent gas, you can find the net heating value of your vent gas at the LFL, which is done by multiplying the 2 terms together. Under the consent decrees, max CC sets a static limit. We have that 270 number or the 380 number. In the consent decrees, the consenters are allowed a flexible limit that is based on the properties of their vent gas, and it's calculated using this formula, where A and B are combustion multipliers that we'll talk about here on the next slide. X is your concentration of propylene, and then you have your net heating value of the vent gas at the LFL. It's not quite the right slide. Next slide. But anyways, those combustion multipliers are in part based on this propylene hypothesis, and we've touched on this a couple times. So this is that idea that, especially when you have you have olefins and hydrogen in the same vent stream that stable intermediates are formed during the combustion process, and that this prevents complete combustion.
When does this slide come back to bite us all in the ass?
Yes.
Yeah, we're just reporting the data.
So-
It's not my flare.
Yes, it's a hypothesis. It's an idea. So anyways, this is where you see the hydrogen-olefin interaction provisions of MAX-EC come from. You know, it's this idea. There's very little evidence to say one way or another. Hopefully, Scott has something to share tomorrow.
If you have to Detroit, those are the only two
Mhm.
places we've
Yep.
Seen this.
So-
or at least published.
So, true or false? We shall see. More testing to come. So here are your combustion efficiency multipliers. It's based on your minimum steam addition. You know, if you're below 1,000 or above 1,000, and whether your VOC concentration of your vent gas is above or below 20%. And it's worth noting here, you know, the methane and ethane are not considered VOCs. So this is anything ethylene or C3 and above. So you have your A multiplier and your B multiplier. Your B multiplier is where you see the hydrogen and propylene come into play. Because the A multiplier, you know, these two variables will determine what your A multiplier is, and then whether you have condition A or condition B for your B multiplier is determined by your hydrogen and your propylene levels in your flare. All of them, with the exception of Flint Hills Resources. BP Whiting, Country Mark, you know, any of them have this formula in them. Yeah, the only one that doesn't have this to this point is the Flint Hills Resources for their Port Arthur facility. They had done PFTIR testing for 2010, I want to say, and their combustion zone limits are actually based on the mass flow going to their flare and the PFTIR testing.
Very good lawyers.
So.
You notice the A multiplier here increases as you go down that list there. The only one that is based on any kind of science is the first one, 6.45. The idea is that multiplier gets you from the LFL in the combustion zone to 300, which is the number we're operating. The 685, 7.1, 7.4 are strictly punitive add-ons that EPA put on because your flare either has more VOC than they like, or it has higher flow, or both. So that's why the A multiplier goes up. It has nothing whatsoever to do with science. It's all about punitive punishment.
So the worst case condition is the 7.4, 4.0, right?
Yep.
Right.
That is the most conservative approach.
Yep.
So that's how most of the DCS programming went that way. Because it got way too wickedly complicated to figure out all these if-then statements, which multiplier we use or not use.
Well, the VOC vent gas concentration is on an annual basis. So, I mean, you know, you
can change that.
Yeah, I mean, all you have to change that once a year.
So. All right. Then when you're actually calculating the net heating value in the combustion zone, you have your vent gas term here and here. You know, and this is where Troy talked about during his MAX-EC discussion. MAX-EC doesn't allow you to take advantage of the combustion properties of the pilot gas. In the consent decrees, that's not the case. You have this PG term is the pilot gas. So it's not a large flow by any means, but it helps a little bit. Yes. These bottom two terms are the steam and air. And so this is fairly similar to what we've seen in MAX-EC then. And then, from a consent decree perspective, your overall objective then is you have 2 points. One is to make sure that your net heating value in the combustion zone remains above the limit you've calculated as we went just through. And the other is to make sure that your net heating value in your vent gas remains above 300 BTU as required by subpart A.
And our experience is if you've got the first, the 300 is easily, you're way over 300.
Usually. There can be scenarios where that's not the case.
Has anybody argued that if you have the net heating value, you don't need the 300 in the vent gas, so we should just dump that? I mean, why? I don't know if anybody...
The negotiator is arguing that point.
Yeah, there's no reason for both,
The 300, at that point, it's irrelevant because you've proven the combustion efficiency and at the tip. So.
I had a question. So with future consent decrees, do you have any idea, whether this sort of
these calculations will stay, or will it go more towards the RTR calculation?
It's a good question. It's kind of one of those things of the refineries are largely out of the consent decrees now. There's probably a few stragglers still to come, but they seem to have focused now mostly on the chemical side. So it's a question of whether the chemical sides will differ significantly from the refiners. The chemicals might be a slightly more consistent vent gas stream because they're coming from specific units. They know exactly what it's going to be. But to this point, it's hard to say for sure. I mean, the one chemicals facility that has the consent decree is markedly different because that's Flint Hills Resources. So whether the future consent decrees mirror that or go down and follow a path similar to Max EC,
Well, one thing a week is doing that is that you notice in the marathon, all the consent decrees, it's a propylene adjustment factor, propylene, because that was the only thing we saw that had the drop off. Awika's now seems to be wholeheartedly embracing and expanding this to olefins. And there's a question whether they're even believing that hydrogen is involved at this point, which means that hydrogen is an advantage because it limits you. If you only have a certain narrow range of hydrogen, if you're outside that range, it doesn't apply. If they take away the hydrogen, then any ethylene, any propylene whatsoever, and you're up to this high number.
Yeah, which means any ethylene cracker is almost automatically in. So, all right. So this is just a quick example using the formulas we've just walked through and a kind of randomly generated flare gas scenario, where you have your molecular weight of each of these components, the volume percent, your net heating value of each, and your LFL of each. And these are just the operating scenarios. You have a pilot gas flow rate of 50 scuff per hour, a vent gas flow rate of 100 pounds per hour with a minimum steam of 500 pounds per hour, so a steam to vent gas ratio of 0.5. And all of this scenario, you have no olefins, so you don't have to worry about the B multiplier, but your A multiplier is that 6.45 because your minimum steam is below 1,000 and your VOC concentration does not hit the 20% mark. So anyways, you have your net heating value of your vent gas, your LFL of your vent gas, and your net heating value of the vent gas at LFL. And they all, my animation didn't work. There we go. I should press the right button. That helps. So your net heating value of your vent gas under that calculation using the percentages we saw earlier is 901. So you're great in terms of the vent gas. Your LFL is 0.04, and your net heating value of the vent gas at the LFL is 34.9. Now to calculate your limit, you have your combustion multipliers here. Remember, methane and ethane are not VOCs. So that means you have a limit of 225.3 BTU per scuff.
Well, except you said that there was no, was there any propylene?
There was propane, I believe.
Oh, so you don't have the multiplier then?
Ah, crap. I got a ways to go back, I guess. You have the A, or you have the...
Yeah, that's if your propylene is...
Well, you have the A multiplier, but your concentration of propylene just falls out because the concentration's 0.
Yeah, so then you're under condition B.
Oh, yes.
So there is no multiplier. There is no...
You are correct. Yes, that is correct.
Yeah, that should be 0.
Yes. It doesn't change the equations because it's still 0.
No, it lowers your limit though.
Yes.
Your NHP changes?
No, because your concentration of propylene is 0,
Oh,
so
see.
B
Yeah,
falls out.
I see what you're saying. You're right.
So, but anyways, so yeah, there you have your limit. So you have your formula for the combustion net heating value in the combustion zone. We do not have any assist air. There we go. So we strike that term out. We have our vent gas flow rates and your mass flow of steam, keeping that same steam to vent gas ratio, and your mass of your pilot gas, which we've used the formula that's found in the consent decrees to convert from standard volumetric flow over to mass flow. MEAT gives you a net heating value in the combustion zone of 591.2 scuff. So that, There's supposed to be something else there, which is great. It means you're above your limit. You're awesome. However, and this touched on a little bit during the MAX-CC discussion. What if you have a system with a flare gas recovery? Your minimum flow to the flare is just your purge gas through the flare tip. So you're assuming a minimum natural gas purge flow rate. A pilot gas, most of this stays the same, which gives you net heating value in the vent gas. We'll assume methane at 896, LFL of 0.05. Your vent gas LFL goes to 44.8 BTU per scuff. Now here's where it starts to get different. When you use those numbers to set your limit comes out to 289 BTU per scuff. And this is where you find your problem. Drop your air out. You have your mass flow rate for your vent gas of only 20.8 pounds per hour, and that's the taking, I think, 500 pounds scuff per hour of natural gas. And then comparing that to your 500 pounds per hour of steam, you have a steam to vent gas ratio of 24.1. Not so good. You have a net heating value in the combustion zone of 52.6. Also not so good. If you look in the consent decrees, there's a table in one of the appendices where it lists the expected combustion efficiency at various net heating values in the combustion zone. If you're below 60, it says you're getting no combustion. So your combustion efficiency at this point is 0, based on that table in the consent decrees.
That's if the steam is influencing that point.
Yes.
They were saying that everything's completely met.
Yes. So
how do the consent decrees handle this? Or do they just say you have to boost fuel gas downstream of your...
There has been much gnashing of teeth over trying to figure out what to do about that.
Negotiating tactic has always been, if it's a flare gas recovery with a water seal, during those periods of non-flare use, the calculations don't apply. So that's the argument, is that we try to argue that the net heating value in the combustion zone, there is no combustion zone, so I don't need to maintain the NHD over the limit.
Well, purge gas is not waste gas, so as long as no waste gas is going to the flare, it's not an operation.
Yep.
That's
So.
the argument. And so far, we've been successful in that.
It's not stated though. Is that documented anywhere, or is that?
Oh, it's in the consent decrees. I mean, there's
Yeah,
a
it's
purge gas
mhm.
and
But in the
waste gas.
MAX-CC, it's not.
MAX-CC is not.
No.
Now, MAX-CC expects sites to go back to the flare manufacturers to try to drop that minimum steam requirement to the point where you can no longer add supplemental gas. Yeah.
Yeah, so the theories have been that as the pressure rises in the flare header, before you bubble through or burp through the water seal, as the pressure rises, then you add more steam to your tip, right? So
Anticipate.
minimum steam is minimum steam, is for thermal, and then as the pressure rises, before you burp through, I'm going to add up to now what you can now call minimum steam.
What the fuck is that?
That's the theory. At the moment, nobody from Zinc or Zico or Calidus has been willing to do that. It adds obviously more complexity to the system.
So, and just for funds, if you wanted to add supplemental gas to this flare that we just looked at, how much gas would you have to add in order to have a steam to vent gas ratio just less than 3? We're not even talking like 1 or 1.5. 3, 167 pounds per hour, which equates out to over 4,000 scuff per hour of natural gas being added to the flare at that point. If you wanted your combustion zone, net heating value in the combustion zone to be above your limit, you need to add 184 pounds per hour, which is almost 4,500 scuff per hour. So, and that takes your steam to vent gas ratio then to 2.44. So you've got to add a lot of natural gas on an hourly basis. I mean, this adds up really, really fast. Doesn't matter how, natural gas is cheap now, but it's not that cheap. So, this is one of those things that, the consent decrees have managed to avoid this, but MAX-CC might really bring it to the forefront.
Consent decrees have managed to avoid this. Avoid what? Avoid having to add a whole bunch of fuel? We don't.
Well, it's because of that whole argument that the flare's not essentially not in operation when it's only receiving purge gas. So it's not, if it's only receiving purge gas, that's not defined as a waste gas in the CD, so they don't, yeah.
It would cost a whole lot of money to get past the
Yep. So, at that point, what's happened is, the flare tip manufacturers have done an awesome job at reducing the purge requirements for their tips. problem is the minimum steam requirements haven't kept up. So those minimum steam requirements are required for the metallurgy and whatnot of the flare tip. And then when you combine them, the results are that. So just a quick rundown of the 7 calculation steps for determining net heating value in the combustion zone. You have them there, so review at your leisure. Now we're going to look at a little bit, this is where I have some fun because my background is chemistry, so we get to go through some stoichiometric equations and whatnot. But what the stoichiometric air ratio is looking to do is determine the molar oxygen demand for the vent gas going to the flare, and then to make sure that you don't add the limit. The limit is defined in a couple of different places differently. The BP Whiting consent decree, which to this point has been the only one to directly address a air-assisted flare, set a stoichiometric ratio of 10. OAQPS's document set a limit of 7. And a third document set a limit of 6, if I recall correctly. So, okay, was it TCEQ? I couldn't remember. So, you can make an argument for being able to use a calorimeter to do the previous equations. But in order to do this one, since the X terms here is dependent on what your constituents are, what the molar oxygen demand for combusting that particular component is, you really need to have a breakdown of all the different components in order to do these calculations. And it's one thing. What these formula shows you is that the heavier carbons, if you remember back to your general chemistry or organic chemistry in college, they require more oxygen to go to complete combustion.
By the way, this is why it's a little confusing to have a BTU and air-assisted flare.
Yep. Because the BTU analyzer will give you a net heating value, but will not actually tell you anything about the oxygen. Without knowing the constituents, you don't know what the actual oxygen demand is for that gas. So this equation takes your molar oxygen demand and converts it to a mass demand. This equation, you could combine these two very easily into a single equation, going from your oxygen molar demand to a mass demand of air, and then you can convert that from there into something from your fan curve or a measurement from an air flow meter to determine how much air you're adding or need to take out of your flare. This is where it looks at the where you need to be operating the air-assisted flare. I believe in the binders this didn't come out quite right. I believe it's just an empty box, but it should be just an X. Not sure why it printed out like that. But anyways, here you have what constitutes good air pollution control practice for an air-assisted flare. TCEQ said 6, OAQPS said 7, BP Whiting consent decree said 10. So we await, and now with the MAX-EC provisions, we don't have a stoichiometric air ratio anymore. So maybe that goes away now. Maybe we never get a better guidance. So, summary of the steps for an air-assisted flare. These are your surrogate parameters. We've just walked through each one of them. And then we saw in MAX-EC, we have even new ones. So this is where MAX-EC comes into play. MAX-EC has the net heating value in the vent gas, the net heating value LFL, and then the combustibles content in your vent gas. That's the new term. That's the total volumetric fraction of hydrogen and combustible organic compounds present in a flare vent gas by volume fraction. So we'll look at that a little bit more here in a second, right now. So you have your formula up here, and it is based on not purely saying you have, say, 10% methane, 20% ethane, 5% propane. So you don't just sum all those up together. This CMNI term here is actually the carbon mole number of combustible organic component I in the flare gas, meaning it is the molar number, it's the molar carbon count really of your flare vent gas. So depending on I believe the combustibles content is based on propane. So that is why this is divided by 3. So because propane has 3 carbon molecules. But in this case, your CMNI for butane or any of the C4s would be 4, and then so on. So that's how that gets factored in there. Now it raises the question though, if you have a THC analyzer, which is just say an FID, burning the gas as it goes by and measuring the ionized carbon atoms, you have no way to get that hydrogen number. Meaning a THC analyzer is really difficult to use here unless you're just going to forfeit that benefit of the hydrogen in your vent gas. So something to think about. Here are your operating parameters. Troy talked about these earlier. I won't go into great detail here. One thing I did want to point out about the dilution factor that MaxEC introduces, the larger your flare, the more it helps you. We don't know the data. We would love to see the data, but that's really interesting. And that may be the case. So, I mean, as your flare increases, an 80-inch flare is more efficient, or is potentially more efficient according to this than a 24-inch flare. So it's a very interesting element of the equation. The same thing holds true for the LFL and the combustibles content. All right, so we went through that one really fast as I could. We have about 15 minutes until the next break, so I'm going to keep trying to go through the control strategies. This is a fairly short module, so I may actually be able to finish it before break, and that way, I know, I have a habit of overpromising.
As long as you don't under-deliver, you're fine.
And that will allow us, when we come back, Scott and Dan will talk about combustion efficiency performance testing. All right. So now that we've looked at how we calculate the stuff from a flare header, we want to talk about controlling those parameters for the flare. This is another one of those cool drone pictures, by the way. So in the control system, what are we looking to control? We have no great control over the flare vent gas flow. That's going to be what it is. It's a product of either emergencies within a refinery or a chemical plant, or just process control in there, and the sweep flow rates. However, can control your steam and air flow rate, and that's really your key element here. So we're looking at your steam and air flow rate and your addition of supplemental gas. So we're looking to automatically adjust for the net heating value of the combustion zone, your steam to vent gas ratio, and maybe even your dilution factors that MaxEC has introduced. The consent decrees have required these parameters to be on an automated control system, meaning that the consenters have a steam flow meter, have a vent gas flow meter. They're pulling data into the DCS system, coming up with a steam to vent gas ratio, and trying to maintain a set ratio. Now, the way most of the consenters have set this up is that you can change the ratio and not be out of manual control. Meaning you can change the ratio from, say, 1 to 1.5. That doesn't constitute taking it out of automatic control. Instead, it's only out of automatic control if you literally flip it into manual and manually set the flare flow or the steam flow rate. None of this is required under JA. JA does not deal with control of the flare. It's only monitoring. So just leave JA in the dust right now. We've just went through all of this. Steam and supplemental fuel or air are the only adjustable variables. And how do you calculate this need for supplemental gas? How do you decide how much do you need to add in order to get above the required values? In order to do these calculations, you do typically need the molecular weight, and this is where it comes into being beneficial to have that molecular weight from the ultrasonic flow meter, because it continuously gives you that molecular weight information. Or you can use a gas composition analyzer and do it through those calculations like that.
Because otherwise you've got too much variability, you can't guess.
Yeah, so, because typically under the consent decrees, the steam to vent gas ratio has typically been on a mass basis. The marathon consent decree allowed a volumetric ratio, but everyone since then has been mass based. So
you can't do mass without.
You need the molecular weight. Like for instance, the optical meter doesn't give you that molecular weight, so you're stuck with volumetric at that point, unless you have another molecular weight
If you have
To-
a GC and it can be
Yep.
molecular weight, you still have a number.
Yep.
But the GC is going to be more prone to problems when you have upsets.
Yeah.
So
Yeah, and the
having
G-
a Nanometrics can give you that molecular weight even if your GC goes down.
You can still keep control of steam to vent gas, even if the GC's out.
Yeah, so and then the GC is also going to have lag issues where it's only going to give you a result every 10 minutes or so, and so composition can change rapidly. So,
By the way, this is one of those interim steps that EPA will ask you for during your consent decree discussion, before you actually sign. Before you install your analyzer, they're going to ask for you to consider, please, a interim step, and being able to use the molecular weight off your panometric flow meter linked to your steam valve will give you at least some steam to vent gas control, and then you can work on that heating valve once you add the analyzer.
Yep.
So this is a common request.
yep,
And of course, if you have an optical flow meter, then you can't accommodate their request.
yep,
You still have to tie the flow into your control system as well.
yep.
Yeah, right, if you have, yeah, a lot of plants have the flow meter, but they don't have the analyzer, so that's why they normally ask for this definition.
Yeah, so, and you can increase that, the runtime of a GC, but your resolution on the peaks of the GC drops significantly. So, there's a trade-off there. You can get a faster result, but you might not know quite as well what you're actually seeing. So this is Troy threw us a curveball when he added this picture in, because we sat there for about 5 minutes trying to figure out what is Troy talking about here. And this is the driving 100 miles per hour down the road, looking out the rear view window, trying to stay in your lanes. So, because when you have a GC, that's what you're dealing with. You're dealing with, well, I know what was in the flare header 10 minutes ago. I have no idea what is in the header right now, but I'm going to adjust my supplemental gas based on what it was 10 minutes ago, not what it is right now. So that's where an instrument like the iMac device or a mass spec, comes into play here, where it's much faster at the results, so you can have much closer to real-time response to these issues. So just from a valve scheme structure, you may be able to add supplemental gas control to an existing purge setup. If you have a second control valve going around the purge gas, you can use that as your supplemental gas addition. It's not generally recommended to use the same valve for purge and for supplemental gas, because there's too much chance of, if the supplemental gas is no longer needed, you can turn off your purge accidentally, so you don't want to necessarily do that. And then there's also the additional possibility of a second level, or third level even at that point, control valve on that same natural gas line for the addition of emergency purge. So if you have a high temperature, high volume flaring event, blows out the water seal, but as that event backs off, you can get cooling in the flare stack. It contracts. It can pull atmospheric oxygen back in as it contracts. So what some sites have done is they add, after one of these events, and they have various stipulations as to what constitutes one of these events, they'll blast in a bunch of natural gas for a very short period of time to clear out the stack of condensable material to make sure it's safe to continue operating. Okay, so supplemental gas addition control. You have two criteria that you're trying to meet here. Three, really, if you add in the max CC requirements. We just talked about maybe that net heating value in the vent gas is no longer absolutely necessary if you're controlling based on the net heating value in the combustion zone. But in the consent decrees, your compliance period is a 3-hour rolling average. Max EC now uses a 15-minute block average, and that's a much faster response, required response time for your system. Because what you're going to see is that if you have a GC with a 10-minute run time, your GC is going to run for 10 minutes, spit back out a result from 10 minutes ago. You're suddenly going to go, uh-oh, I need supplemental gas. Problem is your GC has already taken another sample at that point. So you won't actually see the results of your adding that supplemental gas until the next run, really 30 minutes after the initial event. So that's the problem of flare control in a nutshell using a GC, is that you cannot respond to an event in real time. You can maybe respond to an event if you're in communication with your operators. You say, well, we're about to purge out a vessel with nitrogen. Add in supplemental gas to make sure the net heating value doesn't drop. But in surprise events or emergencies where something happens and that causes the heating value to drop, that's not going to be the case.
That's why they argued and they won the argument to get that 3-hour rolling number in the consent decrees. It's a major victory. So whoever had the foresight of that years ago argued that 3-hour rolling was very, 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 very valuable. But Max CC does not recognize the value that is helping us. So it really is a great frustration.
That was Ruth, and she's here, so everybody can
Oh,
vote.
okay.
buy her a drink tonight.
Yes, buy Ruth a drink.
So anyways, we have the scenarios that would require you to potentially add supplemental gas under the consent decrees in the terms of the net heating value and the vent gas. That may be an issue. Under normal circumstances, that's not going to be an issue for most sites under normal operations. Typically, there's enough combustible material in the vent gas that your heating value stays well above that 300, unless you're purging out a vessel. And you're purging out a vessel with nitrogen or steam, a bunch of material with zero net heating value, going to drop it pretty fast. Now, and it's worth noting that supplemental gas isn't being added to combust the nitrogen, but just to combust the residual VOCs that are also in there still. So, with that, we have talked about these. I will not necessarily go through them again. So you're setting the net heating value in the combustion zone. These are the calculations that we've just walked through. The step 1, step 2, condensed into 4 steps instead of 7. From a max AC perspective, your step 1 is determining your net heating value in the vent gas. And then you have some options, because max EC currently, it has those 3 different parameters you can comply with. You don't have to pick one and stick with it. You can change it based on the profile of your vent gas. If for one period of time, your net heating value in the combustion zone shows you're in compliance, fine. If another, your LFL, shows you're in compliance, that's good too. Or you can use the combustible content. Any of those at any time can work if you have the instrument that can measure that. So that's the key, is that having an instrument that allows you the level of flexibility to use any one of the calculations, which means you have your DCS system or a data handler outside of your DCS spitting these numbers back at it, constantly doing these 3 calculations in parallel with one another to try to keep, monitor each one, and it may turn out, by and large, most of these, if one's in, they're all in. But that won't be the case. There will be scenarios where that's not the case. So steam control, you do have a minimum steam set by the tip manufacturer, and that's, unless the tip manufacturer says it can be decreased, you risk damaging the metallurgy of your flare tip if you don't supply that minimum steam. From a steam control perspective, we talked about control valves for the supplemental gas. From a steam standpoint, typically you want 3 levels of control. You want a restriction orifice doing the minimum steam requirement. You want a small control valve for trim adjustments, small adjustments that may be required, just normal fluctuations in flare flow. And then you want a large control valve to be able to supply the full steam capacity to that flare tip in the event of a large upset. So that is what we've seen commonly. So the CDs require that automated control of steam to vent gas ratio. Max CC does not specify that steam to vent gas ratio. So we'll just keep on moving. DCS control of steam to vent gas ratio. I talked about this a little bit at the beginning. So I have like 3 more slides, so I'm going to push through and finish up.
You got 3 minutes, that's great.
Awesome. Troy said 3, and I didn't know if that meant it was 3 or if I had 3 minutes. So, but one of the problems you can encounter here is if you're trying to control steam to vent gas ratio, and you're trying to control for the net heating value, they can walk each other up if you're not careful. So if you have a increase in vent gas flow, and you have a set steam to vent gas ratio, as your vent gas flow increases, your steam flow also will increase. Now what will happen is if you're also monitoring the net heating value in the combustion zone, that additional steam will cause that net heating value in the combustion zone to drop. And that will trigger the addition of supplemental gas, which will further increase the vent gas flow, depending on where your instruments are positioned, which will then increase the steam, and then you repeat the system. And eventually, you know, if you don't have control or logic controls in your control system,
Max out your steam and your
yep, you have 2 valves 100% open, and there's no telling what's going on at that point. So yeah, you need to make sure that, you know, you either have a control system set up where it's subtracting out that flow of supplemental gas from the vent gas flow meter, or somehow making sure that the steam addition, you don't add steam for methane. Methane is typically not going to smoke. So, you know, it's one of those things, trying to balance the need for steam for the additional vent gas, but also making sure that you limit that steam to the minimum required. I'm going to ignore this because we don't like it. We've walked through all of this. One thing to note, there are instrument manufacturers who will try to sell smoke detecting systems. We have yet to really see one that works. If we see one that works, that would be awesome, but we've yet to see it if it exists. Here's the incipient smoke point. I had a few more slides than I thought I did. This is just a table demonstrating just how complex reality can be for a flare control system. And this is by no means all of the various points you might want to look at. But this is just some of the items you're going to be wanting to record, how you're getting that data point, the source of that data point, you know, the assumption if that data point is bad for whatever reason, and the averaging or rolling total that's applicable from a compliance standpoint here. So, and one thing that Sage has helped several clients do is we've developed what we call DCS calc manuals, which take all of these calculations, put it into a narrative form, trying to help the system integrators understand what they're doing and trying to bridge the gap in between the rules and the consent decrees and the actual programming side of things. This is just an example data path for how your data could potentially flow. You know, you have your analyzers going into a PLC, which sends the data both to a storage system and down to the DCS. You have your flow meters doing the same. So, and
everybody configures this differently.
Yep.
So it really is a worthwhile exercise to figure out where all these little electrons going. Where's the data path?
And one thing we've seen, you know, a couple of sites start talking about is instead of doing these calculations within your DCS, do it external to your DCS. Do the calculations external to the DCS and just spit back, you know, the numbers the DCS needs to control the system. Does it need supplemental gas? Yes, okay. How far does it need to open the valve? That's all it needs to do. You don't need to slow down your DCS doing all these calculations and bog it down with all the data handling. All right. This is the last slide. So this is a chart of steam, vent gas, and supplemental gas from a marathon presentation at AFPM and this conference's former iteration in 2012. And I have modified it slightly to make it easier. I'm red-green colorblind, so I have a lot of trouble reading this. But I've highlighted it. So what you see here, the darker red line is the actual vent gas flow. You can see it spikes here and then trails off and then kind of settles back into a normal flow rate. What you see here is the steam. And what you can see, comparing the two, there's a lag between the vent gas flow increasing here, the steam flow increasing here. Vent gas flow increases here, steam flow here. You know, and then here, we have something really odd going on that I have no idea why they added more steam there. But I do know, however, why they added more steam here. They added more steam here because there's supplemental gas added in. So your steam to vent gas ratio sees the supplemental gas get added in and kicks in steam to compensate for that.
It backs off.
Yes, then it backs off because as it's doing this, down here you see the net heating value in the combustion zone. It's monitoring this at the same time. It decided it needed this supplemental gas here at about 6 minutes. But once it saw, you know, so probably instead of sitting at, you know, whatever their compliance limit was, you know, they had a higher value where it would start adding supplemental gas to try to guarantee that compliance. So it decided at some point to add the supplemental gas. It got back above the limit, turned off the supplemental gas, and it went.
Are you absolutely certain that there was no manual interaction by operators during this?
No.
What you might be looking at is literally just a control cycle,
Oh, yeah.
control
Yep.
cycle that just can't damp itself out quick enough.
Yep.
I mean, quite honestly, that's what it looks like to me. You see that oftentimes in systems like this.
Yep.
Poorly tuned.
If they're not properly tuned, or if you don't even know how to tune them. You know what I mean?
Well, this was an early iteration.
Yeah, this was the first really people to try it.
Timeframe 6 minutes.
Yeah, it's very fast.
6 minutes. You're looking at 8:12 to 8:18.
Yep.
Right?
It is a very fast.
You know, fairly short time.
So, just a few quick issues with flare control. We've talked about instrument lag, the issues with GCs, and how slowly they get the response back to you, and makes control very, very difficult. Valve response time. Just because you've told a valve to open doesn't mean it necessarily opens instantly. It takes a minute to open to whatever percent it's set to, and this could end up exacerbating issues from instrument lag time. And then you have time to tip. If your supplemental gas addition is 200 yards back up in your process unit, it's not instantaneous that it gets to your analyzer or to your flare tip. It takes some time to work its way through the header and get to the flare tip to actually do what you're adding it to do. So, and this gets back to the instrument lag time, where if it takes a while for all of that gas to make it in and to start affecting the combustion at the tip, you can have several more runs of the GC before you actually see the results of your supplemental gas addition. So,
It takes a while if you got a small flaring event.
yes.
You got a big flaring event.
The big one.
It's there, right?
But typically big flaring events don't have the net heating value problems. Those are usually going to be high heating value, not a huge. You're going to be more concerned with adding steam at that point.
You're going to be trying to keep the black cloud from forming over the fire.
That, or trying to figure out to stop the upset.
Yeah.
So, just your conclusions. And next we have Scott and Dan. So, but first we have a break.
All right, so Troy asked me to talk about the flare testing, so this passive FTIR flare testing, which has been in some ways both a blessing and a curse to both the refinery and the chemical industry. A blessing, I think, because it really allows us to understand much more about flares and flare combustion and the effect of assist media than we ever have before. I mean, there really hadn't been any work done since the 80s. And a curse because the EPA kind of ran with this, and now we're having a lot of these things going on, and they're very ridiculously expensive. And I'm sorry about that. Though we are looking at, actually, Yoshing hasn't been here today. I don't know if he was here this morning, but he was sitting next to you, I think, Wilhelmina. And there are several of us looking into alternatives. Before I even get into the test, alternatives to passive FTIR. Yoshing has from Provident, has a thing. If everybody, he's got a paper, I guess, showing some of the results that he has. I encourage you to go down and see that. Clean Air is working on some multispectral approaches to doing this. UT Austin is looking into some alternatives. So there's a bunch of us that are looking very, very hard at looking at other techniques here. But in the meantime, we're going to talk about passive FTIR until we can come up with a better, more efficient way to do this. This is it. So, whoops. Of course, I lose my, oh, there we go. My technology is failing me here. Okay, so, all right. There he is. Hi, Russ. So first of all, why do we want to do this in the first place? Why do we want to do flare testing? And really the only reason is because of the EPA has been very actively visiting folks dropping in on you, and as many of you know who have gotten these 114 letters, they want to know all kinds of information about your flare. Particularly the requests that we've been involved with, they've wanted to go back 5 years, and they want to know what your steam data is, they want to know what composition data you have, they want to know all this stuff. And what they do with all that data is exactly the same thing that Derek went over earlier. They take whatever data you have and they go through those calculations that Derek went through, and they try, based on the best data they have, to estimate your combustion zone net heating value, your steam to vent gas ratios, to see whether or not historically what you've been doing with your flares. It came as a surprise to some folks, because if you look at the CFR in 60.18 and 6311, most of you thought, I'm sure, that I've been complying all along. I've done the things that Derek and Troy had talked about, and these are the headers that, or the sections that are applicable there. Essentially, and I'm not going to go through these because we already did it, there's a visible emissions issue, a pilot flame issue, minimum net heating value, and this is where the difference is. In the past, and we've talked about this all the time, in the past the focus has been on the vent gas before it gets to the tip. Now the focus is on the combustion zone after the assist media is added. And the other thing that they're looking at is exit velocity. So one of the things Troy asked me to talk a little bit about why we're concerned on a flare test with things like velocity. And you can see that because we've gone through the calculations. Why you need to have, the three things you need in order to get the final results in a flare test are your vent gas velocity, your steam, your vent gas flow, your steam flow, and the net heating value of your vent gas. And a lot of these concepts came from these studies in the 80s. There were two studies that took place, and we've talked about them a little bit, McDaniel in 83 and Pohl Pohl actually did three, 84, 85, 86. He was very active and very busy. And the velocity stuff, as we've talked about, came from this McDaniel and Pohl study. You want to know why we're stuck with 60 feet per second and 300 BTU per scuff. You can blame these guys for doing this. In all of the data that they collected in these 80 studies here, I'm not going to use this because apparently my connection is lost, so I'm going to have to go the old-fashioned way here. In all these studies, there are only two data points that were used, that were low BTU steam-assisted tests, which is what we're talking about here. Only one of them here was up at this level here. You notice we're at 60 feet per second and 294 BTU per scuff, which is kind of the 300 we were at. That's the one data point that was used to establish the 60 foot per second, 300 BTU per scuff limit. One test, one data point on one flare. So EPA is always complaining, well, we don't have enough data, to allow you to use pressure-assisted flares. Well, okay, one data point on one flare they used to establish a rule that has affected the whole industry for the past 30 years. So that's where that came from there. Then we have this other limit that came from a Pohl study from 84. You've got the limit of 400 feet per second and 1,000 BTU per scuff. Where did that come from? Well, that came from John's study here. Whoops. Go backwards. Not having much luck with my technology today. There we go. All right, so this is the data that John Pohl put together in 84. And you'll notice here are the points that we're talking about. Here's where the 1,000 feet per second came from. And you'll notice these are the dark black dots. The dark black dots, notice, are a 3-inch flare. This is like a salami-size flare. All right, this is this big. These were the only data points that they got the real high velocity on, and these are the ones that they actually used to establish that other limit, that second number that we have for velocity. Again, one data point, one flare, and the limits we're stuck with forever. So there's the Pohl study, There's the point. All right, so now EPA had a problem. They had this number down here. They had kind of a minimum down here. They had kind of a maximum up here. And now they have a gap. Well, what are they going to do about the gap? They can't have a gap. So they addressed that with, in '86 with a Federal Register notice. And you might have always wondered, and I'm sure all of you have seen this equation here in Federal Register. It's the velocity equation. And you kind of wonder, well, where did EPA come up with this? Is there some thermodynamic thing going on here about flare stability and, everything? Well, it turns out that equation is the equation that connects this dot to this dot. That's all that equation is. EPA had a space to fill. That was the equation that filled the space. Oh no, they knew nothing. They all they knew is that they had a space to fill. Yeah, there's no data. There's no data here. There's only one data point here. There's one data point here. So for the past 30 years, our lives regarding flare velocity have been governed by these two data points. So the conventional wisdom has been, as long as you're in this area, this is the safe area here. This is stability and goodness and high combustion efficiency. This is good. But if you get into the blue area, the assumption is, well, you're unstable. You can't operate there. You're 63 feet per second. That's no good. I'm going to fine you. So that's been the traditional approach. But there's actually no data, or until recently, there's actually been no data up in this area at all, nothing. And there actually was no data. If you look at McDaniel's dot here, that was at 99% or so. This was at 99% or so. So even the data that they had at the edge of this line showed super high combustion efficiency. It's not like they were approaching a cliff or something that they had to protect us from. They were at 99.9% up there. So it's really not about stability or instability. It's really more about known and unknown. So the blue area here has been unknown until recently. We suddenly have some new data to kind of fill in this blue area a little bit here. Let me see. Maybe I took out a slide I shouldn't have taken out here. Hold on. Oh. I took out the one slide that I wanted to show you. Okay, so I'll explain it.
Did you print it out?
No. Oh, I wanted to tell you, some of the slides I'm showing don't exactly follow what's actually in your book, because I added a couple. So in the slide here, in the blue area, the danger zone. All right, down in this area here, we have a whole new set of studies from these ground flares that we've had up in this area that show that you can reach sonic velocity up to 1,000 feet per second. We suddenly have a whole bunch of data points in this area now that show that high velocity flaring, contrary to being bad, is actually good. In reality, EPA should be encouraging us to do high velocity flaring, not discouraging us. If they want to improve combustion efficiency, the way to do that is to remove the velocity limits entirely, because there's no basis in science for for not going beyond 60 feet per second. They were terrified about this liftoff thing. You always see these things about stability, and if the flame lifts off, it suddenly is not efficient. Well, we did a kind of an analysis of John Pohl's data, looking at all the cases where he noted the flame was lifting off and looking at the combustion efficiency. Turns out there's absolutely no correlation whatsoever between flame liftoff and combustion efficiency. None. So the whole fear of liftoff is not valid there. Say again? Well, yeah, if it doesn't come back, it's going to go out. I mean, yeah. At some point, you're going to get to the your exit velocity is going to be greater than your flame speed, and your flame's going to go out.
You're approaching that when you're getting to liftoff, right?
No, not necessarily. I got videos actually of flares that are just humming away perfectly happy with the flame being 3, 4, 5 feet above the burner or the tip, and it's fine. It's very high combustion efficiency. Now, at some point, it will go out. I mean, at some point, that will get far enough away from the tip that it'll just go floop, and it will be gone. But until that happens, the thing is, you have, for high velocity flame, what we found is that you have very high combustion efficiency until it goes out. You don't see the kind of drop off, the gradual drop off. It's high, 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 zero. Yeah, I mean, it is a straight cliff. And so this whole idea of velocity limits is kind of nuts. But that's why we look at things like tip velocity when we're doing these flare tests, because EPA is concerned about that. And again, they shouldn't be. They should be encouraging high velocity flaring as much as possible. This is why the whole pressure assisted flare thing works in the first place. So I just wanted to, that's kind of a little bypass there. So what are the objectives of a flare test? What are we trying to do when we do these flare tests? Essentially, you can't have an instrument. Right now, there is no instrument that you can have that will sit there and look at your flare all day long and give you combustion efficiency in real time. Yu Sheng and other folks are working on this. What do you got? Troy's holding up something. Okay, yeah, I've been pushing for people to go see his paper down there. So Yu Sheng is working on that, and as I said, Texas UT is working on that. So maybe in a few years we'll have a nice little SEMS that you can put on a building somewhere to look at your flare, and it'll spit out combustion efficiency in real time. But until that, we don't have anything. So what we have to do is find an operating parameter that we can somehow correlate to combustion efficiency. We didn't know when we first started this, back in the good old days. When did we start? 2009. There really was, we weren't sure what parameter this would be. When we first did the flare test, we collected all kinds of data. I mean, lots and lots of data. And it took us, 9 months to get a report out on that, maybe even more. I don't even remember how much it was now, to get a report out, because we had to figure out what can we do with this data to correlate it, to relate it to combustion efficiency? What combination of parameters can we look at? And eventually we settled on this combustion zone net heating value. I think the early term was the soup. This was the soup. That was good. That wasn't my term, but it was already in use by the time I got there. So what's going on in the soup? The soup is just all the gas and all the water and everything that's actually going to combust. And it turned out that there actually was a really nice correlation between the combustion zone net heating value and combustion efficiency. Now, it's not obviously it's not a perfect correlation here. This is data from all of the early flare tests. This is Texas City, Marathon Detroit, 2 Flint Hills flares, all the TCEQ data at baseload conditions. This is baseload. There were some non-baseload conditions we tested. You saw those nasty green olefin points earlier. That's not included in here. We'll talk about olefins in a minute. But you can see that, and this was a variety of flare tips. This was a variety of vent gas compositions, and they all kind of followed the same nice line, the same nice curve, regardless of when we first started out, we thought we'd have to do this, that for every flare. Every tip manufacturer would have a different curve. Every flare would have a different curve. If you change compositions, you'd have a different curve. That was the fear when we started out. As it turned out, that was not the case. And this is why not everybody has to do these passive FTIR tests right now, because EPA has also come to the realization that the flares perform pretty similarly. And you can rely on the results of previous tests to be an indicator of the performance of your own particular flare. Now you notice here where this drop-off, I should zoom in a little bit here, but you can see where this drop-off happens at around 300 BTU per scuff on a steam-assisted flare. Now, this is what we found very consistently for all the flares we've done, except until we get to this hydrogen olefin thing. But actually, I'll talk more about that tomorrow. I'm not going to talk about that today. So aside from that aberration, the hydrogen olefin aberration, the results are remarkably consistent. And so what we need to measure here then is, oh, I do have this in there somewhere. Steam flow. Obviously, we need to know how much steam is going to the flare, and this is usually what we found is that there's in most of the places we've been, there's some mechanism for steam, for measuring steam. Most places have an orifice meter or something that we can use to measure steam. Vent gas flow, on the other hand, has been trickier. I'm amazed at all the folks that don't have any means right now of monitoring vent gas flow. This is particularly true, more so, I guess, now in the chemical industry. We found a lot of, like, olefin plants and everything really are not measuring vent gas flow at all at this point. So we've actually had to bring in, we've talked about these optical flow monitors. So we bring in these temporary optical flow monitors. We plug them in, and so we can get an estimate of vent gas flow during the test. Then we need to have vent gas composition in order to calculate the combustion zone net heating value. So that we either rely on the plant GC, if there is one. In a lot of cases, again, there is no plant there. The last test we did, we actually got Dr. Bill Pierman, who you heard from earlier, to bring his fancy new Raman FTIR system. Well, actually, the first time we did it, we brought our own GC, and we did a bunch of GC testing when we had to bring our own. And one of the nitrogen part of the GC, we were getting very unreliable results, and we ended up trying to estimate nitrogen by difference, which was not a good thing to do. And that's kind of spurred the whole idea for this Raman FTIR. Nitrogen was such a problem on this one test. I went to Bill and said, I know Raman can do nitrogen. I said, there must be a way we can figure out how to apply this Raman technology to the flares. And that's kind of where we started taking off on this Raman FTIR. And then the instrument that measures, now this is all process stuff here. So this is all stuff that either the plant has, or that if the plant doesn't, we will bring an instrument to do this. The combustion efficiency then is measured separately, and this is what is measured with this passive FTIR. And this is, Dan is going to talk about that in a little bit. So monitoring steam and vent gas flow, and I'm not going to go, we've talked about this ad nauseum, so I'm not going to go over it again, but we have an ultrasonic meter, orifice meter, optical meter. We have this COSA optical flow meter that seems to work pretty well that we bring in if there isn't one. Vent gas composition, gas chromatography. We've done one test with actually where they were taking bag and canister samples during the entire test. That was an interesting time. There's a lot of samples. I'm sure the lab we took it to was very happy. Say it again?
I was confused. Vent gas composition.
Yeah, I was confused.
Oh, what?
I was thinking we were getting back samples on the flare time.
No. So far, we're only talking about the vent gas here. We're only talking about the vent gas. Now, one thing I found that actually has been fairly handy, I don't have any connection to these people, but we found a nice hydrogen analyzer that we've been using. It's called H2 Scan. It's like $5,000. It's a very cheap instrument. It's Class 1 Div 2. It's very fast. It's very accurate. A couple of downsides. It needs a conditioned sample, so you can't, we found that out the hard way, actually. It doesn't take well to a lot of water. And if you have a lot of CO, you can't use it because CO poisons the sensor. But the two problematic compounds are always hydrogen and nitrogen. If it weren't for hydrogen and nitrogen, we could just slap an FTIR on there, as Bill told you, and we could get real-time data on vent gas composition, but we wouldn't get any hydrogen and nitrogen, and we absolutely need that. This, without even a Raman, this solves the hydrogen problem for us nicely. We still had that nitrogen problem, which is where the Raman came in. And so the testing itself is done by this passive FTIR instrument. Now, this is different than the FTIR we're using to analyze the vent gas, that's a cell-based, it's like a SEMS, you know, there's a sample line, it sucks the vent gas out, it puts it in a cell, the FTIR does its job, and we get a number. The passive FTIR is a passive instrument, and that's the kind of the neat remote sensing piece that we do to actually get the combustion efficiency. And Dan, I think, is going to talk about that. Dan is the one that actually has to do all the hard work. I get involved mostly now with the consent decree stuff, and very little with the testing. And Dan's the one that's out there in 110-degree heat in Tulsa doing this. So why don't you come and talk about this passive FTIR stuff. And he can tell you a little bit more about what actually goes on in the field doing this test. Yeah, I lost my connection on here, so you're going to have to flip it manually. I don't know what happened. Oh, yeah, I'm sorry, you need the microphone. There we go.
Can you hear me? Loud and clear? All right. So I'm going to talk a little bit about what we're actually doing if you're fortunate enough to have us come to your facility and take combustion efficiency measurements of your flare. Like Scott mentioned, we use an instrument called the passive FTIR, and that's very similar to some of the technology that Bill Pearman was talking about earlier today. Essentially, most molecules have a fingerprint in the IR region that can be detected with this instrument. The exceptions are, like Scott said, nitrogen, hydrogen. So we won't be able to see that, those characteristics of the FTIR plume. But as we'll find out, that's not really that important. What we're looking for is basically hydrocarbons, CO2, and CO. And I believe Derek put up a calculation earlier how combustion efficiency was calculated. And what we're doing, we're using that calculation, and we're looking at the ratio of carbon in the flare exhaust, how much of it is CO2, and how much of it is not CO2. And you can use that to determine your combustion efficiency. So I guess before the passive FTIR testing took place, there were a lot of questions about whether it was even possible to obtain reliable measurements of combustion efficiency on an actual real size flare, not some little Bunsen burner in a wind tunnel. And the answer to that question is yes. We've been able to do it. We've been passive FTIR testing, I believe, started in 2009. And we've been doing it pretty regularly ever since, and we've been getting good results. But first, a quick note about measurement. I believe this was from the TCEQ report. They claim that both the AFTIR and PFTIR methods actually compare quite well to the extractive data from the TCEQ test. And there's a little bit of the key word here is methods. So passive FTIR, what we do, it's the instrument itself is not a method, it's a technology. If you were to go and you were to put a telescope on an FTIR and start taking readings, chances are you're not going to get good results. There's a lot that goes into this. As Dr. Bob Spellacy from IMAC has worked tediously over the years to perfect this and to get this to a point where we believe the results. So it's not just as simple as taking measurements. There's a lot of things that go into this. There's a detector. Right now we use a dual detector so that we can see broader range of the infrared regions. And then Bob has worked to figure out which regions we need to look at in detail to determine CO2 and all the other compounds in the exhaust. And there's just, the calibration, the aiming, how the backgrounds are done, and how you treat the data after it's done. That all is incorporated into our technique, and that's what we've been using to analyze the data. So the method is essentially, it was used for basically everything after the TCEQ tests in 2010. That's the method that was validated next with the extractive data that was taken there. And we'll talk about that a little more in a few minutes. But first, so what are we actually doing when we're out there? So you can see there, that's the front of the instrument. We aim it up at the flare. Oh, that's a video. And you can see I don't know if you can see right here, but this is the interior of the instrument, and you can see that little mirror is stroking. So what that allows us to generate is an interferogram. That's just a graph or a little plot of how much signal the detector is receiving depending on that position of the mirror. And then through a mathematical process that maybe you learned about in calculus years ago called the Fourier transform, you can get an emission spectrum. Now what's actually all contained in that emission spectrum? It's not just the flare, right? So we're actually looking at, what's behind the flare in the sky, the air that's between us and the flare exhaust, which we want, and then even the instrument itself gives off a signal. So we want to isolate that flare radiance during these tests. And we do that through a series of daily calibrations. So every day in the morning, we have basically a telescope with a little hole on the back that we can put different calibration sources in and fill the view of our passive FTIR instrument with like a black body source or an IR source or liquid nitrogen for a 0. And that allows us to filter out some of this extra components that we'll see in a spectrum. So here's an absorbance spectrum. You can see where CO is. So after we have this collected, the IMAX software that Bill talked about with the dynamic references and some of the other linearity and fit features is used to analyze the spectra. So you can see the sample on top, that was actually a passive FTIR measurement, and the blue spikes below, that was a CO2 spectra that we generated with a cell-based FTIR in the lab. And you can kind of see, obviously, the computer is the one that calculates the concentration based on the features in that. But you can see there how a passive FTIR spectra that is looking at a plume with a lot of CO looks like compared to just a spectra of pure CO. You can see the similarities, and that's kind of, we're trying to match spectra we collect in the field to references. Now, the passive FTIR does have a few limitations. We're measuring concentrations in ppm meters, we call them. The reason we have to do that is because we're aiming through the exhaust of the flare plume, but we don't actually know the depth of that exhaust plume. There's a lot of turbulent mixing going on, and by the time everything's finished burning, we don't know how deep that plume goes, so we don't know the spread of the components across that section. So we can't determine absolute concentrations or mass emissions with the passive FTIR. We're not measuring that. What we're measuring, you have to remember, is just the ratio of CO2 to hydrocarbons. So why not? Okay. Yeah, units are in concentration times path length, and we don't know the plume
This is
depth.
particularly important to remember if, I don't know if we have time, or we'll have time to get to the AP42 discussion today, but for the flare AP42 factors, EPA took a lot of this passive FTIR data and attempted to do exactly this, to turn it into absolute concentrations and absolute mass emissions. And in order to do that, they made all kinds of assumptions, some of which are pretty questionable. So EPA obviously did not heed this particular slide, that there is no quantitative speciation with the passive FTIR.
So validation testing. So let me just talk briefly about the TCQ test. There were a bunch of different vendors there trying out their various technologies and methods of using those technologies. And really the only one that really worked was the passive FTIR. And the gold standard for that test was this extractive probe that was designed by, I believe, Zach Kodesh at John Zink. And what happened is, it was pretty crazy. I saw it done at a different test. I wasn't at the TCQ test, but we did some other testing there. What was it, a year and a half ago? It was exact same probe, same method, and they have a guy in a crane, first off, trying to aim it over the plume, and then you have two guys on the ground with chains, and they're yanking it every which way, and there's someone out in the control room looking at infrared videos, yelling, to the left, or to the right, and yeah, it was pretty complicated, but you know, it works. Now obviously that only worked because the flare was 15 feet off the ground and not 200. I can't imagine ever trying this on a real refinery flare. I'm not sure you could do this. But yeah, drone. A canister sample?
A canister sample, we'd have either probably a retroreflector mirror on the drone and shoot a signal through the
There's-
flare pool.
You're using your technique for the drone, but I actually want to find out if the drone.
Oh, if you could take an actual sample?
Sample.
That'd be a big drone.
Only 15 minutes, only 15 minutes. You put radiation protection.
You need a pump to suck in the.
Your site?
I would say-
Would you?
Yeah.
All right, I'm gonna take you up on it.
Yeah.
That's your job.
We'll bring the drone. You.
Gotta be able to lift and evacuate it soon.
I know. I said it'd be a big drone.
No, it's 15 minutes, small.
Okay. So again, these were the two methods that were successful at the TCUQ tests. The extractive method and the passive FTIR method. So what we saw at TCQ was pretty much the same thing we had seen in the tests that had been conducted prior to that. We saw, okay, you're humming along at high combustion efficiency until you hit this cliff point at around 300 BTUs per scuff in your combustion zone, and then you fall off. But this was the part that was, or the aspect that was most interesting to us and sort of gave us confidence that these numbers were actually, this is actually what's happening, is the extractive method conducted with that John Zink ear trumpet gave roughly the same results as the passive FTIR, and in fact, the trends are identical.
There's less agreement as you get down.
Yep. As you get down lower, the variability increases across replicates in both methods, both the extractive and the passive FTIR method. So a typical test, if you're fortunate enough to talk to us, we'll start out by talking with you about what exactly you want to know about your flare, and we'll design test matrix to give you some answers. So then eventually we'll have to arrive and set up. We'll conduct the test, and then there's a few keys. If you are going to be testing, there are maybe some advice you want to follow. So the test protocol, what flare conditions will be tested. Sometimes what flares will be tested. We've done some programs where we test multiple flares at a site. What is the length of each test run? Typically, if it's an EPA test, they like to see 20 minutes with 15 valid data points across that 20 minutes. Now, if you're just doing this for yourself or you're doing additional test runs that aren't included in the EPA, the protocol that EPA approved, we can do extra test runs that say are only 10 minutes, just to give you an idea of maybe a different operating scenario if you were curious. So we also, during a site visit, we'll figure out, where are we going to stick these instruments. And Scott talked about what data the facilities usually provide so that we can correlate, the combustion efficiency data we collect to some sort of an operating parameter.
So your minimum test run is 10 minutes?
I mean, if it's in tests that EPA wants done, it's going to be 20 minutes. And they like to see 15 valid data points. So that's 15 points where we have a good view of the flare exhaust from the instruments. Yeah, so if you have a run, let's see, where the wind is just blowing all over the place, changing directions, changing speeds, it might take a little longer, but usually we don't have that issue.
What do you consider stable vent gas BTU, like two GC cycles?
Yes, it's usually 2 GC cycles before, and unfortunately if we're using a GC, by the time the turnaround, it's about 15 minutes, so you only get 2 points during a test. Now, the last test we did, it was really nice. We could tell, we did it with Dr. Pierman, and we knew instantaneously, almost, or within a minute, if something was happening with the process. So that was nice. But where was I? Oh yeah, test length. We don't really have a minimum test length. If you have a steer site and you want us to do a 5-minute test run, we can do a 5-minute test run. If you want an hour, we can do an hour. I don't know why.
So what you're saying is you got to correlate the flared gas with your test facility.
Mm-hmm.
So you have to have measurements.
Yep. So, and obviously, the longer the run, if you can hold your flare steady for that amount of time, which is difficult, you can get more reliable.
And then the business of process gas sampling, you made some comments on that? In other words, if you were to just get process gas sample rather than online analysis.
Like that. Yeah, we did that once.
Yeah, I wasn't there for that.
Pain in the butt for the client because they did the actual gas sampling and they had to do it multiple times during the test. But it seemed at that time that was pre-Raman stuff, so it was the only method that we had available to us.
But you wouldn't do that now, is what you're saying?
We can do it then. The problem is you only get, during a test, then you only get a couple of points. And, if you don't have a stable flare, it's changing. It makes interpretation of the final results difficult. If your flare is really stable during that time, then a bag sample could be fine.
Yeah, the other issue with the GC or the bag sample, well, especially the bag samples, is you don't know till the next day whether or not you had a drastic change in composition during your test run and whether or not it'll need to be repeated. With the GC, if it's online, you'll know, but it'll be after you did the run, and you can't. Whereas if you have a real-time monitor, composition monitor, if something starts happening after 2 or 3 minutes, okay, let's stop. Let's get it fixed, and let's not waste time.
Like any cancer sample,
Yeah.
you've got sure what your subnodal cancer is going to be the same thing taken out in the lab.
And then with Dr. Bill's technique, it's just a hot sample, heated sample line.
Yep.
From the,
From some point on the flare header, usually after everything's had time to mix. You pull that down through a heated pump, through the instrument, and depending on what it is, you can either vent it, because it's a small flow rate, or if you have HCN in your flare vent gas, for example, you're going to want to put that back in. So that's what we had to do at the last test. But yeah, overall, I thought having Bill out there to do the online analysis worked very well for us. And we got a good 3 weeks of it. So we were able to iron out all the kinks too. Okay, so back to test planning. Obviously, we need to power trailers. So like any other stack test, you need to have power available at the site locations. Fortunately, that's just on the ground for us. You don't have to have power up 150 feet in the air. We can just, we bring in trailers. Well, I'll show those in a bit, but yeah, we basically just need to power up the trailers that house the instruments and the engineers. And also we'd need data transfer capabilities between the locations, just so that we can monitor what's going on in one trailer at the other and vice versa. So when we get to the site, there's lots of equipment to unload and set up an initial calibration. It can take a few days. We've gotten it down to the point where we're really only setting up one day. We're always just waiting on plant electricians, and you know how that goes. I spent 3 days last summer waiting for plant electricians to hook up my trailer. The whole time we were ready to go and paid for 3 days worth of passive FTIR testing because we weren't allowed to hit the on switch on the generator. So, yep, sometimes things go that way. So we get, like I said, you want high data transfer capabilities between the two trailers. So you'll need some sort of Ethernet or optical cable. We need clean power. I prefer generator power. Just personally, just get a big generator. That way, you know it's steady. We had one test where clearly it was not clean power. There were all kinds of surges. One guy was sitting there and he was getting shocked every time he typed on his keyboard. So needless to say, the computers were fried by the end of it. And we were changing out motherboards and instrument electronics, and we had to run over. This facility was kind of in the middle of nowhere, so we had to drive 2 hours one night and back to get more computers because ours were all fried. So, and we set up our trailers approximately the same distance, or that's the height of the flare, because we want to be looking at a 45-degree angle optimally. But we want to kind of stay within 800 feet because eventually you lose its signal over that long of a distance. So another thing we do during tests is if your facility has a control room that we can all sit and look at the data, that'd be great. But if not, we can bring another trailer. We'll set up a big screen TV with a bunch of video feeds from each instrument location, and you can watch the process data. Someone from the plant will be there, so you can watch that in real time and see how it reflects the visual characteristics of the flare or the IR image. It's pretty cool.
Actually, at each, there are two cameras.
Yep.
There are 3 cameras in each location. There is an infrared camera, a visible camera, and then an aiming camera that's actually on the massive FTR. It shows you exactly where the flare plume is pointed. So at a 2-location site, you've got, this is why you need optical cable. I mean, the bandwidth is fairly large to get all those video images to a central location. And the idea is if there's any glitches in the data, we want to have an idea of what was visibly going on with the flare during the glitchy data, in addition to having the process data.
Okay, so arriving on site. So we also have these calibration carts I talked about for the. It's basically inside that box where you can see the two guys working. It's basically a telescope, and we want to set that approximately the same distance that the flare is from the instrument, because that will then more accurately reflect any transmission losses in the air between between the instrument and the flare when we're collecting the emission spectrum. So the reason we have two instruments at a test is to accommodate the wind. You can see sort of an example right down here. This is ideally what we're looking at. The wind is blowing perpendicular to your instrument, and you can see clearly downwind of the flare exhaust. You want to be about 1 flame length away from the flame, so you can be sure all the reactions have stopped. If you're too close, your signal will be too hot. There'll be unburned hydrocarbons. If you're too far away, it'll be too cold, and you'll just get a 0 reading, even though it's clearly burning, you can see. So a bad view would be this example here. If the wind is blowing, directly in line with your instrument, you can't really see downwind of the flame. Or if it's blowing straight to you, you don't get a good view. It's sort of like, go ahead.
So, go back. There, that's your target.
Yep.
So if you were doing 1.5 inches towards the flame, or halfway between there, your data wouldn't mark that one.
Like if I was right here, let's say.
Okay, then it's not as good. So let's move a little bit to the left, in the mid. Go to the right of the X. Okay, now to the left a little bit. Left. Okay, right there. How would your data be right there?
Not as well.
What kind of variability do you have where your data's good and where your data's not?
We actually have done
It's like this.
We have diverse, close, and far. There's actually a fairly broad region.
That's what I was hoping to hear, because otherwise
Yeah, you don't have to be on that spot perfect. You have some leeway in where you can be measuring, and your results are still very consistent.
The key here is when you see these things here, these are indications of areas where combustion is still occurring.
Yeah, you want to dodge the little flamelets.
This is why you need an aimer. Because as these things move out, you don't want to be sampling in here because there's still combustion going on. There's unburned hydrocarbons. So you see the aimer kind of moving out, coming back in, moving out, coming back in. So you're getting kind of spatial averaging as well as temporal averaging on here, and they're also kind of moving up and down.
Yeah, the aimers just do a good job of always keeping it moving in that general vicinity and dodging the hot white flamelets. Yeah, the best aimers also play a lot of video games. No surprise.
The same thing goes for the probe, the extractive probe. It doesn't want to see those flame out.
Right.
Yeah. Yep. But yeah, we get a guy that's good at video games, and they have to have a crane operator and 2 guys pulling on chains. So.
The probe could be a lot farther away because it doesn't care if it's sampling a cool stream. We're relying on the
That's true.
of the plume to get a signal. So we can't move too far away, or the plume gets so cold that the signal noise goes to hell, and then we can't do it. So there is a sweet spot that's pretty broad.
So is it going to be about a meter above beyond the?
Well, it really depends on how big your flame is. If you have a ground flare burner, pressure assisted, where you have a 60-foot flame, we don't need an aimer. We just let it sit there. Yeah, that flame's going straight up, and it's huge.
A wide range up there, and still.
We get the same answer. Yep.
So the temperature you're looking at that point is what?
Well, again, it depends on what's in your flame, but it's usually around 250 C, and that's another good indication, which I can't give the secret away for. That's patented. How can we get the temperature? from that. But that's one thing that Dr. Bob over at IMAC has been able to figure out.
That's a critical component.
Yep.
Being able to accurately measure because the
Concentrations,
concentration.
yeah. So when you typically, if you have a cell-based FTIR, you heat your cell up to a certain temperature, and you compare it to references at that temperature. So it's very important when you're using any sort of FTIR technique or method that you have an accurate indication of what temperature is.
So it's that temperature, combustion reactions will stop.
Yes.
Yes.
That's the idea.
Yep.
We want to take it so the combustion is complete as it's going to get, but it hasn't cooled off enough so that our signal disappears. So that's why we have.
I mean, your signal's based on the molecules vibrating, or the temperature of the.
Well, yep.
It's all about collecting the radiant.
Yep. So we couldn't do this on a cold stack to measure like a typical stack test. If it's a cold stack, we can't.
Because the molecules aren't vibrating as fast, or to give you this.
Think of it as
Well,
a
yeah.
flashlight.
Yeah.
There's an infrared flashlight up there shining at you, right? And if the batteries get too
Yeah.
run down too far, then it's not going to shine at you. You can't measure it.
Yeah.
It's the energy coming from the radiant energy coming from just past that.
Yeah.
Well, still, I guess,
Yeah.
just past the combustion zone, right?
Right.
Yeah, okay.
Yeah, like we've done a few tests where we've looked at just validation of this, looked at, hot furnaces or thermal oxidizers, and we can see CO, for example, little trace amounts of CO in that because it's hot coming out of those sources.
Actually, that's one of the validation tests we do, if it's available, is if there's a stack that has a CO and CO2 monitor that's hot, like a heater or something, we can shoot across that, compare the results we're getting from the SEMs that are on that stack, and then do a calibration to that.
Sorry to delay.
Generally works out pretty well when you do that.
Yeah, I got a lot of that data.
Yep. Okay, yep, so if you happen to poor wind conditions, you may be trying to take a picture of a horse's head from the wrong side. And your data may be suspicious. So this is just an example. This was at Flint Hills, just locations and blind spots of each of the instruments. So you can see how we set them up at a 90-degree angle. That way, no matter what, which way the wind is blowing, we have a good view of the plume. Actually, at the first test, I wasn't there, but we ended up having to throw out a lot of the data because we set up the instrument, and on some days, the wind's blowing away from you. It's nothing you can do. So if you do want to do multiple flares and they're fairly close together, we can try and position one of the instruments where it can see both and then just worry about moving one around. So again, this is just a windrose plot. And I'll use these after I get back to my desk. And so say I'll find the minutes of the test where the data was collected in that blue bad region.
That's your own met data.
Usually the plants have wind data just for safety reasons, like releases and everything. People need to know where to go. So we'll use that supplied by the plant. So, and that's a good check. And a lot of times if there's a funny point in our combustion efficiency measurements, it'll be correlated to a minute where the wind is not optimum. So during the test, we either have one or two engineers in a trailer, one with just kind of making sure all the mechanical things are working and aiming the instrument, and one person crunching the data, making sure the spectra and everything look good, and sort of conveying that back to wherever the plant people are. So we do these field calibrations every day. Again, there's another view of our telescope. Sometimes, unfortunately, maybe the hardest thing about figuring out where to place our instruments is we need a lawn, straight aiming region on the ground to do the calibrations. It's pretty easy to just aim up. You can shoot over most things. But getting a clean view of our cart from a long distance can be hard in an actual refinery. So you'll have to close down the road for a few minutes while we take a measurement. But everywhere we've gone, it's been pretty doable. We've been able to reroute traffic for a few minutes or whatnot. And during the test, we're taking before and after each run, we're splitting off the flare and taking backgrounds of the sky just to make sure it hasn't changed. And that we're getting the right radiance removed from the emission spectrum based on the sky conditions.
So cloud moving, big dark cloud moving,
No, because we'd be aiming at that big dark cloud during the background. Ideally, yeah. And let's say during the test. Well, not necessarily, because then what we do is on our post background, we would take a background of the cloud. And then we would, during post-processing, we would figure out what minutes you need a sunny background and what minutes you need a cloudy background. So yeah, we talked about all this data that needs to be arranged. And yeah, it's easier for me if I can arrange a format in advance. That way we can just set up spreadsheets to calculate everything in real time and get you the results you want right away. And this is sort of what the TV screen will look like in your control room or war room or whatever you want to call it. You'll be able to see feeds from several different cameras simultaneously, and along with process data. So keys to a successful flare test. If you do find yourself having to conduct one of these, get everyone involved early, from the plant manager all the way down to the operations folks, and let the electricians know we're there. So we're not sitting around for a few days. Yeah, and we have a lot of downtime during these tests while we're actually waiting for the flare to achieve a stable condition that we're trying to test, because some of the operations people, all they do is adjust the steam. That's all they're used to doing. So they're trying to make sure certain compositions are targeted and hit, and if they haven't practiced that before, it can be difficult for them to do that quickly. So if you're going to do this, I'd recommend having your operations folks and practice. And calibrate your instrumentation. If you have we found out, I think someone mentioned earlier, one of the tests. Yep. That we had an 80% difference between what the flow meter was saying and what Tracer Co. came in and told them the flow was saying. So at first we thought they had a completely magic flare. And it turns out it's kind of just like the rest of them. Yep. And I think that's all.